Okay, let's go ahead and start to reconvene. Okay, let's see, some housekeeping stuff. As I said a minute ago, if you came in late, please do make sure to register before you leave today so we can get a good count of folks and in part help to justify to do this again, hopefully. Let me see, let me talk a little bit about timing. So I skipped over a few things and we didn't get to the breakout solutions in a couple cases. So I think what we're going to do is we can talk through some of the breakout problems now. I'll talk a little bit about merging, which was what I had left essentially from Module 3. And I'll do an example of reading in sort of messy data into R, which was what was essentially left over from Module 2. These will take the place of Session 4, which in the schedule was going to be the first session this afternoon. And then we'll go to Session 5, which is Jacob's session on programming and for loops and functions. And the other Chris's section 6, which is on doing analyses, I guess. I forget exactly how we framed the topic there. And then I'll try and work Session 4 in, which is basically sort of how to use and work with R packages. I'll do some of that tomorrow. So I know sort of the time got away from us a little bit this morning. I apologize for that. As I said, this is the first time we're doing it, so I'm still trying to gauge how long everything will take. And I know, for some of you that we might be going quite fast, so I do encourage you to, ask questions, in the chat room or, wave your hand to people, or to ask questions now. So before I get to the breakouts, are there questions that folks have from this morning about how to do things or things that people are confused about or whatnot? Everybody's totally happy or just not willing to speak up in a crowd of 150 people? Yeah, Vanessa.
I was wondering if there's a way to view the raw data set in R, kind of like, I work with data before, so there's always the viewer window.
Yeah, so I sort of tend to just do what I've shown you of just doing like head or picking, if I want to see 100 rows, I'll just do vote if that's my data frame and then give it 1:100 and that'll print out the first 100 rows. There is actually a viewer sort of like a spreadsheet. I'm afraid I'm going to forget how to do that. Does anybody know how to do that?
You just double click on it over.
Okay. Okay, so you're saying if I double click on this, it'll open that up in a spreadsheet?
Single click.
Huh?
Single click. Just clicking once on the running.
Oh, okay. Clicking once works perfectly. Thank you. Okay, so here it is in the form of a spreadsheet, if that's the sort of thing you're looking for.
Yeah,
Yep.
that's what
Right.
Okay, thanks.
Okay.
But it shows only the first 1,000 rows, it doesn't show the whole thing.
Say it again?
It just shows the first 1,000 rows, it doesn't show the whole thing here.
Okay. Is there a way to see the other rows?
You have to basically select those rows.
Okay. Actually, this brings up something I want to mention that Jared might mention tomorrow when we're talking more about sort of scientific computing practices, which is one principle here is that you not manually modify your raw data ever, except by script. And the reason is if I go in here and I don't know if I have the pick capability to go in here and change this manually, but I would in a spreadsheet. If I go in here and I just change it, the 2 to a 1.5, there's no record of me having done that, right? So if somebody else comes along and they get the raw data, their raw data is not going to be the same as the data set that I then have that maybe I send along to them, and there's no record of me having done that. So the principle is that if you're going to change the data, that you basically read in the raw data, and then you have a script file, your file of R code, where there's a line of code that changes, the third column, fourth row from a 3 to a 2 or whatever, and you do it by script, and then you've got a reproducible workflow that you can see everything that's been done. And if you give them if you give them raw data or show them the URL of where the raw data was coming from, and you give them the script, you're showing them exactly what you've done. So that's one of the principles in terms of reproducibility. Okay, other questions from this morning or more generally? Yeah.
What's the difference of within and with?
That is a good question, and I may not be able to answer that off the top of my head. I think within is a way of taking, say, a data frame and doing an operation in it and modifying the data frame, and then you basically return, I think it basically resulted as returning the modified data frame that you can then assign. Christina's nodding her head. Good, I'm happy with that. You can basically say, when you say within, you can do some operations on the data frame. The result is a new data frame that gets returned out that you then assign to a new variable. With with, so maybe since Christine seemed so confident, maybe you can explain. Do you know what with does that's different than within?
Yeah, with will just work with it. Like it's kind of like attaching the data frame, sort of like that. So you can just reference things like inside the data frame.
Okay.
Or turn back the same way. Whereas if you use within, you always get the entire data frame back.
Okay.
Like with the modified column.
Okay, so if you use within, you can basically create new columns, whereas with, you can't?
Yeah.
Okay. And then you know, there may be more to it than that. I've used them. I don't use them a huge amount just because I never started using them, and they're nice things. I just never got used to using them, so it's sort of not on top of my head exactly the differences. But again, and the help, you know, help should be helpful. The help information. Other questions? Yeah.
It seems like sometimes in places where you would think there would be a string, like if you say like library, you actually just write the raw name of something that doesn't exist and it treats it like a string.
Yeah, that's a good question. Let's do, so library is a way that we load a package, as we've seen. And if we do help on that, let's look at the help and see what it says. So it says the first argument is the package you want to load. It says the name of the package given as a name or a literal character string or a character string. I'm not totally sure how to interpret each of those pieces, but that's basically what you're saying. You could either say foreign without quotes or foreign with quotes. It's a little beyond what I can answer at this point in terms of what it's actually doing if you give it the word foreign without the quotes, because there has to be something more complicated going on behind the scenes in terms of processing that. Yeah, my answer is not very satisfactory. There are cases where you can do either and it's fine, and if you can't, you'll generally get an error message back and you'll realize you have to switch to a character string, for example. I think oftentimes it's probably safest to give it a character string, but that's sort of me talking off the top of my head. Other questions? Okay, so let's look at a few of the breakout solutions. What I've done, actually, let me give you 20 seconds to do this. I have pushed the solutions to the first 3 breakout sessions up to the GitHub repository. And so what that means is you can just go to the GitHub repository, which is probably written somewhere, but I think I can reconstruct it from scratch. GitHub.com/berkeley-scf/r-bootcamp-2013. If you go there and click on modules, you should see a folder called Breakout Solutions, and in there you should see the individual files for the breakout solutions. So that's probably the easiest way to just pull down those R markdown files individually. If you figured out how to do a pull of the Git repository, you can also just do a pull, and that should get you the breakout solutions folder as well. So let's look at, go back to module 2. I'm going to load in these guys here. Okay, so the question said, with the that voting data set, I want a new column where instead of that age 9 column, which was this factor variable that gave the lower and upper bounds of the bin of ages that the person belonged to, I want to convert that to a numeric value which is the midpoint of the age range for the age group associated with each person. So instead of 25 to 29, I want this person, who's the first person, to have 27, this person to have 21. 21, is that right? Yeah. 21 and the midpoints of those ages. So if that's the challenge I posed to you, what are the sorts of conversions that I need to be doing here?
Probably need to like split each one into like strings for each number and then convert those to numbers.
Okay, so and actually there's even a step before that, which is what form is this variable in right now? It's a factor. So I need to get it to a character string. Then I need to do some sort of string manipulation to try and get the 25 and the 29 and the 18 and the 24 out. Then I need to get it to numbers. Then I need to do a little bit of arithmetic. Then I'm done. So that's the sort of, sort of thing. As I think about a problem like this, I'm thinking, okay, what sorts of operations do I need to do here? So that's indeed what I'm doing here in the solution. So first I'm going to say, let me just convert that and overwrite the current field and make it a character string, a character vector. So now age 9 should be a character string instead of the factors. And now I'm going to do something. If I look at the unique variables here, I realize, all of these are in the same form, except this one's a little bit going to be awkward to work with. Right? So I could either leave those folks out if I didn't want to have to deal with that, or I'm just going to make a sort of default choice and say, I'm going to truncate, I'm going to say 75 over is essentially 75 to 99, and I'm going to do a midpoint on that. So I'm just going to overwrite, I'm just going to take I'm doing, this is really frustrating. Occasionally it works, and usually it doesn't. I'm going to do a subset operation on the vote age 9 vector, and I'm going to replace that subset for which it's 75 and over with 75 to 99. And now I should be able to do my substring operation, which we saw when we were working with strings, of I'm going to get a vector of lower values, which is first to get the substring, the first and second characters. That's going to still have it be a character string initially when I just do the substring. And then I'm going to convert it to numeric with as.numeric. Right, so the as functions, it's basically as dot whatever you want it to go to. And in this case, numeric makes sense. And then to get the upper end of the interval, I need to skip the minus, and I need to get the fourth and the fifth characters. So I'm going to do that. That's interesting. I wonder if that means that some of these guys were NAs. So I redid it, and that was different. I think what happened was, I think I never ran this line of code actually here. Is that correct? And so as a result, when I did the upper, it was trying to take the, it was trying to convert some of this to a numeric. It was pulling off the fourth. I'd forgotten to run this line of code. So when I got down here to upper, and it was finding things like this, it was trying to take the fourth and the fifth ones, which were the O and the R, and then it tried to do an as.numeric and said, I don't know how to do that. And that's when it gave me some NAs. So if I just went back and redid everything, I'm no longer getting that warning because of the fact that I converted the 75 or over to 75 to 99. So things look okay. So now I'm going to create a new field in my data frame that has this approximate age, which is just this midpoint of the bin intervals. And now I can go ahead and do a histogram, which in this case is sort of a bit of a silly histogram, I guess, because I've only got these discrete levels. But it does just illustrate what happened, and it hopefully illustrates that it's at least plausible that my code here is correct, and that it seems like it's done something sensible. So in terms of error checking, it's often nice to just be able to make a plot and just make sure you haven't gone too far awry, too far wrong. You can often just see by visual inspection that things sort of make sense. Okay, questions about that? Yeah.
So I tried to get the lower and the upper by using a string split icon.
Also a good idea. Yep.
Into numbers, but when I add a character and then I give it the string split, it says I don't have a string type.
Huh.
I don't have a character string.
So you did something like, oops, temp gets, see if I can do this on the fly, string split of vote age 9. Is that what you did? And sep is that?
Yeah.
Okay. So let's look at help on string split and see.
So it's split.
Split. Okay, so I had the wrong argument name, so that happens a lot. So let's see what the dimension, oh, that's interesting. So temp, so I'm guessing it's a list. Yeah, well, wait, what is this? That is a list, okay. So it's a list of, and what's temp of 1? Okay, so it is, so we would, if we did it this way, we'd have to do some sort of processing of the list of the sort that we saw with that double square bracket business to try and separately pull off the 25, or the lower parts, which are going to be each of the elements of the list, and the upper parts, split them off into 2 vectors, and then, or, actually, as I'm thinking about this, there's another way to do this.
I applied as number and then the mean.
Right, so you should be able to, each of the elements of the list, say this one in particular that we are looking at, you should be able to apply a function to this vector that converts it to numeric and then takes the mean of the 2 values. So I think I don't want to take the time to actually write that out, but that should work.
Well, my problem was actually earlier, I guess my as characters and work with
Your particular one, as opposed to mine?
I don't know.
Yeah, it's possible it might be something earlier on in your code than that your object is somewhat different than mine or something. Anyway, I think I'll skip on from here, but if you want to ask one of the helpers, we can look at that more specifically. Other questions or comments? So actually, that was a good illustration of in general, there are going to be 5 different ways to do things that involve more or less coding, more or less efficiency, more or less clarity in what the code looks like, and it's sort of somewhat a matter of personal style. Other questions or comments? Okay, so let's look at problem 2. So I said go back to slide 6 on logical vectors and figure out what is going on in the last few lines of code. So let's actually go back to that. So I'm gonna, looks like I don't have module 2 open at the moment, so let me open that. Of course, if I don't have the slides, it's gonna be, if I don't have them actually as slides, it's gonna be harder to remember what is slide 6. Right, does anybody remember where that is? I guess I could search. Here we go. Okay, so this was, so I gave you this bit of code. So let's look through this. If I say answers and update, that gives me this vectors of trues and falses by Boolean logic. But another thing that I could do that would give an equivalent result is I can say as.logical of answers times update. So anybody want to throw out a suggestion as to what's going on here and why I get the same result? Yeah.
Before you multiply answers and updates, I'll go into the 0 or 1.
Yep.
And since false is 0, the and sign will be 0 if either one of them are false.
Right. So I can do this sort of Boolean arithmetic as actual arithmetic, because if I multiply falses and trues together, the falses and trues are going to get coerced to being 0s and 1s, because that's what R is going to do behind the scenes, because when it sees a multiply, it knows it needs numbers. And the only time I'm going to get a true is if I have a true and a true, because that's the only time I get 1 times 1. Otherwise, I get a 0, because if I have at least one false, I'm going to get a 0 multiplied by either a 0 or 1. That'll give a 0. So this gives the equivalent. This is going to give me 1s and 0s, and then if I do as.logical, it's going to convert it back to being trues and falses, so I get the same thing. Or is a little bit different. So if I do answers or update, I get true, 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 false, false. If I do answers plus update, you were just talking about we were multiplying, the result of the previous operation was going to be multiplying 0s and 1s. Here we're going to add 0s and 1s. So if I have 2 trues, I'm going to get a 2. If I have 1 true, I'm going to get a 1. 0 trues, I'm going to get a 0. So I get that. But if I convert it to as.logical at this point, it's going to evaluate 0 as false and anything other than 0 as true. So it's now going to give me back that the 2 is a true, the 1 is a true, the 1 is a true, and the 0 is a false, which is the same as what I had here. So there are various ways, if you sort of understand what R is doing behind the scenes, that you can basically sort of do math on these Boolean variables. Okay, any other comments or questions? All right, let's look at module 3. Seem to be scrolling out. Here we go. Okay, actually, let's go look at the slide because that has the actual math in it. Okay, so I said, okay, in statistics, there's this chi-square statistic that's used for doing a hypothesis test of whether two categorical variables are independent or not. I don't really want to talk about the particular test or what's going on with it, except just as a way to motivate why we might want to do a calculation like this. So this calculation, at least if we explicitly look at it and were to translate it into coding, we would have two for loops looping over two separate indices, and then we would be doing the calculation of the elements with respect, the calculations with respect to the elements of y and e. And we'd have to do something in advance to calculate the EIJs that might involve doing some looping as well, because we have to do some summation of either rows or columns. So the point of this was to say we don't need to do any looping to do any of these calculations. Okay. So let's actually now go back to the solutions and see how we can do that. Okay, so first, well, maybe I guess this is just the full solution and not. So let's the first part of the I sort of was trying to lead you through the question in pieces. So if we had the Y matrix and the E matrix, both of them in hand, then all that we saw on the slide was we just need to subtract the elements of each of the matrices, square them, divide by the elements of the E matrix, and then do a sum. Right? So all of this can be done on the full matrices without doing any looping, because I'm just element-wise by element. I'm doing a subtraction, I'm doing a squaring, and then I'm doing a division, where I'm dividing a whole matrix by a whole matrix element-wise. So if you recognize that, then that is what this line is here. So so suppose I have the E matrix already. The Y matrix is the matrix of counts for the data. I can just take the sum of subtracting the two matrices, squaring the resulting matrix, and dividing by the other matrix, and that's just one line of code without any loops. And then the creation of the E matrix is basically if I have so yi dot by the notation I have in the slide is just the row sums, the sum of each of the rows of y. So I can think of this as being yi dot. I guess I don't have to write the dot. I'm actually writing, huh? And this is y dot j. So row sums, column sums. If this were y, I can sort of represent this as being the sums of each of the margins. And I can just do that with the row sum and column sums functions that I mentioned, presumably in this module. And then if I want to do the pairwise product of this by this, this by this, this by this, this by this, et cetera, that in mathematical terms is an outer product. And so it's just doing sort of pairwise multiplications of each of the elements of each of those two vectors. So I can do that as this outer of yi dot and y dot j. And then if I go back to the slides, recall that in the denominator, I had y dot dot, which is the sum of all of the y values. So that's just a scalar. So I can do the outer product and then divide by the scalar. And, oops, that's not what I wanted to do. So indeed, I can create that E matrix just with this line of code. So that's pretty clean. I don't have a lot of looping. If I'd done this sort of just with looping, I might have ended up with like the double for loop and then maybe a loop for doing the summation and whatnot. And I avoid all of that here. And this is hopefully fairly clear in terms of what it's actually doing. Any questions about that? So if you, the sort of take-home message here is if you see loops, think vectorization. Don't think for loops unless you really need to do it, unless you really are not able to think of a way to do it without looping. There's a slight caveat to that, which is the other thing that we need to be aware of is just if you're writing code, how much potential is there for introducing bugs by trying to be slick in your coding versus just doing everything sort of very verbosely. So there is some, one other way to approach this kind of thing is write it out the way that seems most simple and straightforward and maybe quite verbose, and then write it out in the way that is slicker and more clean and maybe more efficient, and then make sure you get the same result, and then you have a good idea that what you've written in the sort of more slick version is correct. Okay, so then I had a question that said, what about a sort of stratified analysis for each combination of sex and education level in that earnings height data set, find the second largest value amongst all the people in that group uniquely identified by sex and education level. So this is the sort of thing that we saw you could do with, we saw by and aggregate, where we're going to split up a data set, do some sort of operation, and get the results back. So we can take our earnings data set. There are a few different sort of ways you can use the syntax in the by function. So here, if I give it a list that has the variables that I want to split it by, then that will also do the splitting. And then what am I doing to get the second largest? I'm going to make another one of these anonymous functions, just make it on the fly, use it, and get rid of it. And so I'm going to sort, the way that I got the second largest was to sort in decreasing order from largest to smallest, and then just take the second element of the resulting sorted vector. Okay. And then that's just going to return that to, in whatever format the by happens to produce. So we can look at results and see what that looks like. So it returns it back in this sort of awkward format. I forget if I said anything here. Yeah. So sometimes this will happen in R that you'll get stuff back and it's sort of in, you're not quite sure what format it's in. There's a lot of attributes. And if we do a class on, oops, on that results object, it says it's a by, it's a class by, which we sort of haven't seen before. I haven't actually worked with it very much, so we're sort of not really sure what's in this sort of complicated object or how to manipulate it. So sometimes it just helps to just sort of play around with sorts of functions that you think might be helpful in terms of sorting through things. And so in this case I said, well, what's the dimension of results? Well, okay, it looks like it's sort of in the form of something that looks like a matrix. It's a 2 by 19 dimensional thing. It's got all of this additional attribute stuff of all that information that we saw here. But if I do results of the first row, it does give it back to me in something that looks like it's giving me the results presumably for the first in the two categories of sex. And so then I was just playing around and I was like, well, maybe I can just make it into a matrix. Well, that didn't work. It still gave me back this sort of ugly formatted thing. So then I said, well, what are the attributes of the results object? So it's got some dim name, it's got a dimension, it's got dim names for the rows and columns, which are just character versions of the numbers. It's got this information about what created the object, and it's got the class information. So this is probably not the best way to do things, but it occurred to me to maybe I can just tell it to be a matrix and see what happens. And if I do that and then I look at results, indeed it now actually takes the form of a matrix with some attributes in it. So in this case, that would actually work, and I can then do results of 2, say 12, and get out that one. That was a bit of a meandering. I guess my point in that was if you get back something that's sort of complicated, feel free to just sort of play around with it and see what you can do, and you may just need to sort of finagle things to try and get it in a format that is useful. Or perhaps better, you could go and look at the help information on by and see if there's some useful information in the help information as opposed to just sort of blindly stumbling through as I have here. Okay, any other comments or questions on this one? Okay, so let's go back and just look at a couple of those things that we left out. So let me go back to Module 3. I think the main thing I left out was merging. So I want to just talk through that briefly. Let me see what else. Oh, right. We talked about sorting. I did that fairly quickly. Were there any questions about this idea of creating a vector that gives you the ordering and then using that vector to then do the ordering of a data frame or a matrix? Did that seem really confusing, or that seemed okay? Okay. So let's look at merging. So this is basically, if you do database stuff, this is basically just a database join. Okay, so I have two data frames. They have some column in common that is the key field on which you're going to do the merge, and you want to pull the information from one data frame into the other data frame by matching on this key column. So for example, in the voting data frame, that voting data set is a bunch of information that's at the individual level, one for each person. But each person is associated with a state. And there's lots of state level information like what's the size of the state, or how many people live in the state, or what's the average income in the state. And maybe you want to pull that state level information into the individual level data that are in the vote data set. Well, we would need to do that by having a common column or common field from the voting data set with some state level data set that we have. So there's a bunch of pre-processing here, which is often the case when you're trying to merge stuff. You need to sort of get the columns to be the columns that you need, and the naming to be similar. And if they're factors, you need to make sure that the factors in the key field in one data set and the factor in the key field in the other data set have the same number of levels, even if some of the factors are not represented in a given data set. So I don't want to go through all of the machinations that I did here to sort of set things up, just because it's a lot of just sort of pre-processing. But the idea is that after all those machinations, I end up with the vote. Oh, I manipulated the vote data set to have it have explicit state names in it. So remember before it was this sort of awkward data set that just had numbers for the state IDs. And then it has all the information on the individual voters. So I manipulated it to make sure that I now had a state name field in the data set. And then there's this data frame, or I think it's actually a matrix in R called state.x77 that has a whole bunch of information about states from 1977. So again, this is obviously a toy example. But I manipulated that so that I then had a state info data frame that has, as you can see, these happen to over here just be row names. They're not actually a field in the data set, so that I'm not able to merge based on the row names. I need to have it actually be an explicit column. So here's the actual explicit column with the names of the states. And then here's the state level information that the idea is I want to merge this into the voter level, the individual voter data. So the basic way you do this is you use the merge function and you give it the two data frames that you want to merge together. So here's the vote with the state names and here's that state info. And in this case, I'm taking state info and just choosing a few of the columns, so I don't need to merge all of the columns in. I just decide I wanted to merge in the name, the population, the income, the literacy rate, and the life expectancy. And then you need to tell it what are the columns that are in common that you want to do the merging and the matching on. So the by.x is the name of the column in the first data frame that you're going to use as the key field, and then the by.y is the name in the second one. And then all.x and all.y are basically that you're often going to be in the situation where one data set has many more rows than the other data set, and maybe the first data set doesn't have all of the states represented. So do I want to merge in all of information from all of the states or just the states that are represented in the personal level data? And those sorts of one-to-many and many-to-one kinds of relationships. So this says I want all of the records from the first data set, the individual voter data set, and I do not want all of the records from the state level data set unless the particular state is represented in the individual level data. So that's the basic idea there. And you do want to be careful here, and I think I'm maybe not being as careful as I should, with making sure that being careful about whether we're merging based on columns that are factor variables or columns that are character variables. Because it looks to me, when I look at the state level data set, it looks to me like these are being treated as factors because they're not in quotations. So I'm a little worried, if I were doing this for real, I'd be a little worried that I'm merging based on a factor variable in one data set and a character variable in another data set. I think in this case it works out okay, but that's something I would want to keep in mind in a real data analysis. So the result of that, I created this full vote data frame that has sort of the full information, and if I now look at the dimensions of each of the data sets, you can see I still have the same number of records, but now I've got additional columns, which are the columns from the full state level information. Okay, so that was a sort of quick introduction to merging, but hopefully it gives you a flavor of that. Any questions about that? Okay. And then the last thing I was going to talk about before we move on to Jacob was, I guess this was in Module 2. Is I wanted to talk about reading data in when the data are kind of messy, because that happens all the time. So let's just see an example of this, and a little bit more about reading data in generally. Okay, so we've already said you need to make sure you know where R is looking for the data, the data file with getWD and setWD. So you need to sort of make sure that's all set up. So then there are a few sort of core functions in R that will read in data from sort of standard flat text files where you've got rows and columns, and each of the columns is separated, say, by a comma or a tab or a space or something like that. So the main function is read.table, and read.csv is sort of a special case of that reads data sets that are separated by, where the fields are separated by commas, which is a pretty common format. So this is a data set that I didn't give you guys because it's really big, but it's one that I have on here on my machine, and we'll just walk through and see what are some of the sorts of things that arise when we read in a real data file. These data I think are from, if you guys have seen the website Kaggle, which is sort of this website that sets up competitions for doing statistical modeling and machine learning and prediction. So this is a data set of, I think it's like times on some Australian freeway of like how long it takes different cars to make their way between different segments of the freeway or something. Okay, so I went in and I said, okay, I see that's a CSV file. Each of the columns is separated by commas. And I just looked at the raw data file, and it did have a header row that indicated the names of the columns. So you can sort of interpret what the arguments are here to the read.table. And I just sort of went blindly and said, let me just try this and see if it works. So let me just look at the first 5 rows and columns of the data set that gets read in. Okay, it doesn't look too bad. It looks like it's read in some time information that seems to be in this first column, and it's got some numbers in these other columns that correspond, I think, to the timing of the cars on this freeway. And I don't quite know what these names in the columns mean, but okay, maybe I'm willing to proceed regardless. And I might check the dimension. Okay, 120,000 observations, 62 different columns, so looks pretty good. So let me do another check. So what I'm going to do here, I skipped over this before, but I'm going to say lapply to that RTA data set and tell me the class via the lapply. So remember, a data frame is also a list. If I do an lapply to a data frame, it's going to do that operation on each of the columns, because each of the columns is the elements of the list that is the data frame. So I'm asking what class is each of the columns, just to sort of do a check. Yikes, everything's a factor. Right? It looks like numbers, but they got read in as factors, which is really probably not how I want to be analyzing timing data of cars on a freeway. So something went wrong here, and this is often the case that R will try and be helpful and read stuff in as a factor, and it'll turn out that's not actually what you wanted. So this then generally would lead you to looking in the help information and saying what tweaks can I make in terms of the arguments to the read.table function that would override the default operation. So it turns out there's something called strings as factors. By default, something that R recognizes thinks is a string, it's going to read it in as a factor instead. So I'm going to say in this case, no, don't do that. If you see something you think is a factor, instead treat it as a string. So it's going to do that. It's fairly big, so it might take a few seconds. Depending on the kind of data to get read in, it sometimes takes more or less time to do the same reading in, depending on how it's interpreting the different kinds of values. So now if we look at, say, the third element of this result, it is actually a string, which is not surprising because I told it to read stuff in the strings instead of factors. So that's still not quite what we want because we're thinking these are numeric values. So there's something in some of these columns. Usually R would just read in stuff. If it saw some stuff that was numeric, it'd read it in as numeric. It's not going to by default read stuff in as character strings if it doesn't have to. So something's going wrong with at least some of these columns where it thinks that the only way to handle it is to read it in as a character string. And indeed, if we do that same trick of looking to see what the fields are, it says, oh, they're now characters. So one way we could look at this is go back to the original RTA data set that I read in where there were all those factors and say, what are the different levels of the factor? Why is it that some of these are being treated as not as numeric variables? So this is sort of the process that I would go through. And if you look at this, you see, oh, you know, there's some stuff that looks like it's missing. There are things that look like numbers. And wait a minute. Somehow now there's an X in some of these columns, right? These columns look like they're numeric, but every so often they have an X. So presumably that whoever made this data set, their flag for missing values was an X. I didn't happen to know that when I read the data in, and this X, R runs across it and says, X looks like a letter to me. This must be a character field. I'm going to treat all of it as characters. Or in the previous case, I'm going to treat it all as factors because by default I'm trying to make things into factors. So there's another way to deal with that, which is to say, okay, again, I went back into the help and said, oh, you know, there's a way to tell R what are the things that should be interpreted as missing values. And so here I'm telling it, na.strings, you should interpret anything that is actually na. There presumably aren't actually any of them in this data set because it's not actually an R file of any sort. Or treat an X as missing values. So after this sort of iterative process, we can then read it in now to RTA3 is the third version of me trying to read this in. Again, it's taking a few minutes. And now if I check the type of the different fields, at least these ones that I specify here, it does indeed say they're integers. So it seems like I finally, after this long iterative process, have had some success in reading this in. And I could go through and, you know, if I were reading this in for real, I would then want to do some checking and make sure that the X's got converted to NAs and see what happened to those strings that were empty and see if those got converted to NAs and just sort of make sure that, do the bookkeeping to make sure that everything seems to have been read in appropriately. This is also a good point to say that perhaps before doing all of this in R and going back and forth, I might have just sort of been able to scan through the data as a flat text file and gotten a sense for what was going on, and maybe I could have avoided some of those steps. Let me skip to the slides version just to say a few more things about reading data in. So that was module 2, I think. Yeah, so there are other ways to read in. You can read in line by line. That's this read lines function, and it's just going to read everything in as a character string, and then you can use string processing to process it. If you have data sets where each of the columns is a fixed number of characters, like say the first 5 characters might be an abbreviation for the state, and the next 2 characters are, I don't know, some number associated with the state or something else, there's a read.fwf for fixed width format. And that's useful. We've already seen using the foreign package to read in our case, we read in Stata data sets, but you can read in SAS data sets and lots of other different kinds of data sets with the foreign package. And R will handle lots and lots of other different kinds of file formats, like netcdf is popular in atmospheric science, so I end up working with that a lot. So there's an add-on package to deal with that. In general, in sort of scientific computing, we try and discourage people from using Excel as a way to store your data because it's not really a data storage format. It's more of, it's a spreadsheet, and for the reasons that I have here. So if you're storing data such as that, I strongly recommend you just store it as a CSV and not as an actual Excel file. And then we've already seen a few ways you can write data out from R. We can write out objects using either save or save.image. There's an analog to read.csv and read.table that will take a data frame and write it out as a comma-separated file or as some other delimited file. And then there are a couple other functions that can write out in other formats. And then the last thing is, you'll see this tomorrow, but we can, instead of just creating a plot within our graphics window in R, we can actually create a PDF or a JPEG or a TIFF or something like that from R that we would then embed in if we were then creating a document. And the standard way you do that is, in general, for any given kind of file format, there's usually an analogous function that will create the graphic in that format. So there's a PDF function, there's a JPEG function, there might be a TIFF function, there's a PNG function. And so you just give it, darn it, you just give it the name of the file you want to create. You can give it some width and height information, and then you do the steps to make your plot. And then this dev.off stands for device.off. So it basically says, okay, I'm done writing stuff to that file. You can go ahead and close off that file and make it a legitimate, coherent file. And that's going to then create this PDF file for you. And then this is just a bit that I'll let you read on your own. If you want to take like a matrix or data frame in R and make it into a table in HTML or make it into a table in LaTeX, if you use LaTeX for document processing, you can follow syntax here for doing that. So you don't have to manually transcribe from R into whatever document processing that you're doing. Okay, so I think that sort of cleans things up from this morning. Are there questions about any of what I just covered, or other lingering questions? Okay, so let's switch to Jacob. He's going to talk about programming. So that's going to be probably a little shorter than some of the other modules. We'll do that. There'll be a breakout. We'll take a break, get some snacks, and then the last session is that Chris will talk about doing analyses, and that'll be the last session of this afternoon. So come on up, Jacob.
Okay, so we're just going straight on?
Yeah.
All right, hi everybody. I'm Jacob. All of the stuff that I'm going to tell you, Chris has already done, sort of in passing. So that's number one. Number two, if you've programmed before, all of the stuff we're going to be covering is kind of very basic. It's how does R implement very simple programming structures. So the title of this section is programming. Of course, I'm going to be up here for like 30 or 40 minutes, and programming is something that a lot of people do like for a job. So we're not going to cover all of programming. Just a few very simple things.
Or if you did, we should pay you a lot of money for
Okay, so one thing that Chris has already covered is this idea of an if-else statement. And so basically all we're going to be talking about is controlling the flow of your program, making it do what you want to do. So this is the basic structure of an if-else. You have an if statement, and then you have a condition inside parentheses. If the condition evaluates to true, then the block that follows the if statement is evaluated. Okay, so if val is less than 0, this will print out something val is negative, and if it's not, it'll print out something else. So if the thing inside the condition is not true, then it'll go into the second block here. It'll go into the else block. So let's go ahead and run that chunk. Okay, so we generated a number, negative 1.7-ish, and indeed, it went into that first block and printed out that the value is negative. And that's an if-else statement. They're as simple as that. You can go slightly more complicated and chain them together. So here we have an if, and then we have an else if, and then we have an else. And one of those blocks is going to be evaluated here, but only one. So if we do the same thing, generate another random normal vector. Here we've generated one that's negative 0.9. It's not less than negative 1, so it'll proceed down to the else if. The absolute value is indeed less than 1, so it's between negative 1 and 1. And so the middle block here is being evaluated. So val is within 1 standard deviation of the mean. All right, if-else statements. And then another thing that Chris has talked about is this question of what is true or false. And so he talked a lot about a number which is not 0 is always true. So we would see that if we ran this little block of code here. we would see that indeed 3.1 is interpreted as true. You can use that as you want to do all these tricks that Chris was doing, although, using numerics as true or false values is not usually super useful. And then one other interesting thing is that the string true is in fact evaluated to true. Which I kind of learned this when I was playing around with this the other day. But the string bear is not true, but it's also not false. So you can't turn the string bear into something logical, something that's interpretable as true or false. Okay, so that's if-else statements. Loops. Basically, Chris spent the entire morning bagging on loops. Loops suck and never use them. And this is true, as you said, like 99% of the time. But for the 1% of the time, and also my background is that I'm not a statistician. I kind of come into this from the programming side, and so I'm this dumb guy that's always trying to write a loop and then realizing after the fact that you can do it smarter in a kind of vectorized way. So I'm going to teach you. I'm going to dangerously teach you how to use loops here. Of course, computers exist, programming languages exist, and computers exist because computers are much better at doing lots of boring stuff than humans are. And that's kind of what a loop represents. It's do this boring thing many, many times. Okay, so abstractly, this is a very abstract way to put it. So what you're going to say is for variable in sequence, evaluate that statement that's inside the block, statement or set of statements. So you have to have some kind of a sequence. That's a list. That's a vector or whatever kind of data you're putting in. And then for each element that's in that sequence, you're going to use that element somehow. And that is a for loop. So here's a sort of concrete example of that. So we create a little sequence going between 5 and 20 in steps of 5. And as you can see, we said for I in my sequence, print I. So the first time through, I was 5. The second time through was 10, etc. So we printed our way through this sequence. Almost all of these examples will be the wrong way to do it. I'm not going to show you any cases where a loop is the right thing to do.
Actually, let me interrupt here at this point, which is the times, sometimes you just can't get around to doing a for loop. The other thing is the times when it's fine to do a for loop is if each individual step of the for loop is a really large body of work, so if it's some big regression that takes 2 minutes, and you're doing a for loop where there are 15 things to do, there's not much overhead in doing the looping there, because most of the work is being done in the actual body of work in the individual iterations of the for loop. On the other hand, if you're doing a for loop where there's not very much to be done within each iteration and you're doing over very many iterations, that's when it's going to be really slow and inefficient to use the for loop. So that's a little bit of guidance on sort of big principles.
Yes, that's exactly right. And of course, we can just put the sequence directly in as we do in many cases. Okay, so that's one kind of loop. There's one other major kind of loop that you might use called the while loop. The while loop has a condition, and every time through the loop, it's going to evaluate this condition. If it's true, it's going to execute the statements in the body of the loop, and then go back to the top and check again to see if the condition is true. And so what this means is it's pretty easy. Okay, so here's a quick example. So we initialized I to be 0, while I is less than 10, add 1 to it, and print it out. So this is just another way of looping through the integers. What this means is it's really easy to create an infinite loop with a while loop. So I can do it right here. If I change this plus to a minus. I don't remember how to break code in.
Try escape.
Not escape. Okay, escape eventually worked, or else it just got tired. So as you can see, I create an infinite loop. I'm subtracting 1 from I each time, and so that means I is always going to be less than 10, assuming you started less than 10. Okay, so here's a couple of examples of cases where loops are maybe not the right thing to do, but are the way that I tend to think about things first. Okay, so the Fibonacci numbers, you guys are familiar with the Fibonacci sequence. You start with 0 and 1, and then the following elements in the sequence are you just add the previous 2 numbers together. And so that's what's happening here, and I'm doing the thing that Chris said not to do in his talk earlier today, which is that I'm sort of creating this sequence on the fly. So I'm creating a new vector every step of this loop. And this is the thing that ends up being very slow if you do this 50,000 times. But of course here we're only going to 12, it doesn't really matter. So for each step we initialize it with 0 and 1, and then for each I in the sequence 3 through 12, we set my sequence of I equal to the sum of the previous two in the sequence. And as you can see, we do indeed get the Fibonacci sequence here. All right, we can do sort of a similar thing with a while loop, except here I'm using probably too much code to do this. But I want to print all the Fibonacci numbers less than 500. I don't know exactly how many that will be. It'll be maybe 12 elements or maybe 15 elements or 16 or something like that. And here I don't have to know in advance. The while loop is saying, while the current value is less than 500, keep on with the loop. And so module all this initialization stuff and the stuff to keep track of where we are in the loop. This is exactly the same thing that we did in the for loop. So we get the Fibonacci, all the elements of the Fibonacci sequence less than 500. Okay, there are a couple of very basic elements of flow control that you can use when you're inside of a loop. First, there's this statement next. And what next does is when you're running through the loop, it breaks you out of the current evaluation of the loop and skips straight to the next one. Okay, so what's going to happen here is we're printing out the elements in the sequence, the numbers in the sequence from 1 to 10. But on the 5th time through the sequence, we say if I is equal to 5, next. And what next does is it skips us out of that loop, and so it doesn't execute the print statement. It just goes straight back to the next iteration of the loop. So you can see we got the numbers printed out 1 through 10 with the exception of 5. So this can kind of be useful when you're doing something that's a little bit logically complicated. And then break does something, is a similar way to control the flow of loops. The break statement says if you hit the break statement, the loop immediately ends. You stop iterating through the elements of the for loop, you stop iterating through the while loop, and you just hop right out of the loop right then. So what I'm doing here is I'm generating random normal variables and sort of summing them all up on the fly. So if I generated a 1, you start out at 1, then I generate -1, subtract it off, we're back at 0. So I'm adding up a bunch of random normal values of variables. And when the sum of that sequence of numbers that we've generated goes above 3 in absolute value, we stop. And so what I'm printing out is the value that we reached, which here is 3.5, so we stopped, and I. So you can see it took 13 steps through this loop to break out. So we could run it again. That time it took 6 steps to break out. And you can see here I've used this kind of dangerous thing while true. True will always evaluate true. And so what that means is we're depending on this break to happen to get us out of this loop. And notice that in principle, of course, we don't ever have to exit this loop. If we keep generating zeros, for instance, we would just never get to a sum that was greater than 3 or less than -3. So this potentially could be an infinite loop. But y'all do statistics, right? That's pretty unlikely. Okay, so I'm gonna skip over this avoid loops disclaimer because I feel like we've got it enough. You can do things vectorized. You can use built-in functions. You can operate directly on vectors very easily. And frequently this is indeed faster. Okay, so that's kind of the first set of things that I wanted to go over, and those are all kind of just basic control flow. If else and loops are things that have been around in programming since the beginning, of course. Okay, user-defined functions. So we've been using functions, of course, all day. In general, what functions do are they take some kind of arguments as input, and then they return something as output, usually, or they just do something and don't return anything. So for instance, a plotting type of function might not return anything. It might just do something like put a plot on the screen. But frequently, usually, they return something. Okay, and so there are two sort of main reasons to define your own functions, and those are reusability and clarity, as it says up there. If you find yourself typing out the same bit of code several times, usually that means you're doing something wrong. Usually that means that you should take that bit of code and put it into a function and then just call that function several times. You'll save yourself typing, and it'll be clearer when you're reading through what's going on, what is actually happening. So that covers both these.
It also reduces the amount of bugs you'll have in your code, because if you type out the same thing 3 times, there's a pretty good chance that one of those is different than the others.
Yeah, or if you type it out 3 times and you go back and you change it 1 of the 3 times, but you don't change it the other 2 of the 3 times, then you could be getting results that are unexpected. So earlier here we were doing this thing where we were checking if these various objects evaluated to true. We discovered that the string true evaluates to true, the number 3.1 evaluates to true. And so you'll notice here, of course, we typed out the same thing a whole bunch of times. We had an if and then something, and then the same block was being evaluated 3 separate times. And so what we can do is we can turn this into a function. And this is the general format for defining your own functions. And this will probably be the most useful thing in this part of the boot camp. So to define a function, you have whatever you want your function to be named, and you're going to assign to that name a function. Okay? What goes inside here are whatever you want to be your program arguments. The arguments to your function. So these are the inputs to your function. And then at some point in your code, you're going to output something, typically. You're going to return something that's the result of some calculation. So in this case, what you can see, we're taking this argument val. If it's true, we're going to return a string that says val, whatever you put in is true. And if it's not true, we're going to return something val ain't true. And then what you'll see is if you have an error in that logical evaluation, it actually returns neither.
So I'm used to Python, and is there some kind of namespace type thing, or do you have to concern yourself with the variables you use when you're trying to program?
Yes. So the question is basically about scoping and what variables you can use at any given time. And so I'll talk briefly at the end of this module about what variables you can access at what point in the code. But yes, there is scoping. There are scoping rules. Okay, so what you can see here is we've defined this function and then we've called it 3 times. So as Chris was saying, if we wanted, we could make one change to that function and then run it 3 times again, and the change would be made to all 3 evaluations. So false, it turns out, is not true, the string false. And then again, bare, it gives problems. Okay, so a couple of things I wanted to note here. So number 1 is that R is loosely typed. Notice we defined a function, but we didn't say whether the thing we were passing was going to be a string or going to be a numeric kind of a variable, or even a list or a vector. You can define in functions, of course, to take either of those. It just, any kind of, functions by default will take any kind of an R object. And they're happy with that until you try to use it in a way that object doesn't want to be used. And at that point, it throws an error. Okay, so it lets you call the function when you pass it this string bare. But then when you get to this point, if val, it says, okay, we can't evaluate, we can't interpret bare as logical, so we're going to throw an error. Okay, so this is what is meant by loosely typed. You can define a function that takes some kind of arbitrary object, and you can either just assume that the thing that's being passed to it is the right thing, or you can do some sort of a check on the class of the object or on the type of the object to determine how you want to handle that type of object. Here, I'm just letting it throw the error. Okay, so that was number 1. Number 2 is how do you actually return results to wherever you're calling the function from? So I've kind of demonstrated 2 ways of returning results. One is through an explicit return call. And I think that this is probably the best coding practice to use, to explicitly have a return statement that returns whatever thing you want to return. So in this case, a string. And so when you get to the return statement in a function, the function immediately ends. Nothing that's after the return statement gets evaluated. You go home carrying the value that's the result of the function. But there's another way to return values back, which is just whatever the last statement in your function, the last statement that like gets evaluated, that's returned as the return value here. So right here, you know, if we just evaluated that code by itself, right, that's just a string. And so when you evaluate a string at the R console command line, it just prints it out. But in the context of a function, you're evaluating the string. It's the last thing that you evaluate through the course of the function, so that's what gets returned. All right, so I personally think that this is kind of a confusing way to write your functions, that just whatever's on the last line gets returned. So I think it's probably preferable to put what you want to be returned in an actual return statement. It's easier for the person who's like reading your code after the fact to figure out what's going on. Okay, it actually turns out that there is one more way to return the result of your function, and this is what's called invisible. And the context in which this is used is like, say, as in this example, you want to do something that's like graphical. So you want to like put a plot on the screen. So I'm defining this function that's called histNormal. It's going to take a number in. We're just going to assume it's a number. If it's a string, it would throw an error. And we're going to generate in random normal values and then plot a histogram of them with the hist function. Okay, but then invisibly, as it were, we're going to return the maximum of that list of in random normal variables that we generated. Okay, so if we define this here, okay, so now our function is defined. So if we just run this histNormal, it's just going to plot a histogram of, in this case, 1,000 random normal variables. But nothing happened with that max vals. Okay? So we didn't assign the result of that function to any variable. And so that max just got dumped into the ether. All right? So we forgot about it. What we can do instead is set max equal to histNormal, where max is a terrible variable name. Let's call it max val, because there's a function named max.
Why is it a terrible variable name?
Yeah, we don't want to mix up. I may have totally screwed up the namespace. Yeah.
So there's a function named max that's built into R. So I'll probably talk about this tomorrow a little bit, but naming stuff that's the name of the standard R function is sort of confusing in code.
Okay, and let's print out max val. Okay, so we assigned max val to the result, the invisibly returned value that histNormal returned, and indeed it's equal to 3.85, which is sort of plausibly the largest random normal in a sample of 1,000. So invisible is used when you want to return something, but you don't want it to like automatically be printed out if you just run that function. You want for the end user to have the option of like catching that and using it. Okay, and then as we've seen before, of course, you can have multiple arguments. And here, what I'm doing is setting default values for the arguments. Okay, so I'm going to define this silly little function. It takes 3 arguments. It takes a number. We're going to do something to this number and return it. If that number is greater than some threshold, or the way I've written it, if it's less than some threshold, we're going to divide it by some other argument modifier. Okay, so all 3 of those, the number, the threshold, and the modifier, are arguments to this function. But if it's greater than the threshold, we're actually going to multiply it by the modifier. Okay, there's no reason for this function to exist. This is a silly thing to do to data, but it is a function. So let's go ahead and define this here. Okay, so what's going to happen when we run new function of 2.6? What's going to happen is that 2.6 is going to be assigned to num, num being the first of the 3 arguments. And then the second and third arguments are just going to retain their default values. Threshold is going to be defaulted to 0, and modifier is going to be defaulted to 2. All right, so since our argument num is greater than 0, we're going to return the modifier, which is 2, times num. So we're going to get 5.2 is going to be the result of this function. Okay. R is very lazy in how it matches arguments. So it just goes left to right. So if you pass it 2, and the function called for 3 arguments, it's going to assume that what you meant was to pass it, the first thing that you passed was the first argument, and the second thing that you passed was the second argument, and it'll just keep it'll use the default value in this case for the third argument. Okay, so in this case now 3 becomes the threshold. It's not a very good laser pointer. Right, so our second argument was threshold. Because 2.6 is now less than 3, what we're going to get is 2.6 divided by 2 instead of 2.6 multiplied by 2. Okay, so indeed 1.3. And then finally, you give it 3 arguments. It'll just put them all in a row. Okay, but then if we want to, we can switch up the order in which we call these arguments by actually assigning them specific names, passing them in a named way. So here, notice we're calling them in the reverse order that we called them before, but because we actually pass them the names, because we tell it we want the second argument to be actually the modifier argument, we'll get the same result that we did with the reversed arguments previously. Okay, so default values are useful. All of the R functions that we've been using, like rnorm, has default arguments. So if we call rnorm without any arguments, well, with let's say 0 arguments, okay, it doesn't have any default for the number of arguments. So let's say we want 1 random. Let's say we want 5 random normals. Right? Well, we're getting our random normals with mean 0 and with standard deviation 1 because those are the default arguments that rnorm uses. If instead we want the mean to be 3, we can pass that in as the second argument. And if we want the standard deviation to be tiny, we can, if we want the mean to be 3, but with a small standard deviation, we can pass that in as the third argument. All right. So rnorm and like all of the functions that we've been using all day today are using tons of default arguments behind the scenes that are like optional that you can pass in, but in general don't have to. Okay. So notice that new function had several arguments. Okay. So when you use this function sapply, right? Sapply takes in some list of values, a vector or a list, and then it applies some function to all of the elements in that list. Now that only kind of makes sense if your function only takes 1 argument, right? So that the function is each time it's going each element through the list, it's just operating on that element, which is just like one thing. So by default, the functions that you pass to sapply just take 1 argument and just use 1 argument of the function that's called. So if we just if we evaluate this. This calls new function and sends all these random normal variables in as the first argument to new function, but the threshold and modifier that we defined before, that we gave default values to, it just uses the default values that were predefined in the function. But if we want to, we can pass those arguments through to new function as well. So here I'm explicitly doing it in the context of sapply. So sapply lets us pass in extra arguments, and those will be passed through to the function that's being called. So here I'm going to use modifier equal to 1, and recall that we were either dividing or multiplying by this modifier. Of course, dividing and multiplying by 1 are the same, and so what that means is our random normals go through unmodified. All right, so we've set modifier equal to 1, so we didn't actually do anything to that whole list of random normal values. Okay, and so what sapply is actually using behind the scenes here is this ellipsis argument, this triple dot. Okay, so I used hist here, but let's go ahead and say args sapply. All right, what you'll notice is that it takes x. X is whatever list or vector of things you want to operate on. Fun is the function that you're using. But then there's this dot, dot, dot. Okay? And the way that this dot, dot, dot is typically used is if you pass extra arguments into sapply, those dot, dot, dot arguments will be passed through to the function that you're calling sapply on, that you're applying to this list of values. Okay, and so that's how sapply does it. And of course, we can do the same thing. We can write a function that has these dot, dot, dots. One context in which you would use this is to pass graphical options. That's pretty common. Okay, so what we're going to do here is define a function called a hist normal wrapper that just kind of wraps the histogram function. Okay, and we defined it to take a number in. We're going to assume it's a number because otherwise our norm is going to have a problem with it. We generate in random normal variables. And then we call hist with that dot, dot, dot as an argument to hist. Okay, and so what that means is that, okay, so we can call the dot, 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 we can call this function with no arguments. And it just does a histogram as we expect. But we can also pass through an argument into this dot, dot, dot that will get passed straight through to hist, right? And our function doesn't really have to know or care about what kind of arguments are going to be passed through to the underlying function. It'll just, any extra arguments beyond in are just going to get passed straight through into hist. And so one thing that you might want to do is breaks to plot more bins in your histogram. So here we're going to plot 50 breaks. So like I said, this is something you'll very commonly want to do if you're plotting graphics and you want to define a function that does some interesting stuff and then does a plot, but you want to be able to control the plot options.
Does that do named arguments or only like positional ones?
I think it only does named arguments. I don't think there's any way it could do positional arguments.
It actually does positional.
Oh yeah? Yeah, okay. I don't know what the order of the arguments are that are passed to the hist function. And so
maybe that's more dangerous.
yeah, so in general you'll want to use named arguments when you're using this, this ellipsis. Okay, and then one other thing that, that Chris mentioned before are these anonymous functions. And this is the idea that you're just defining a function that's kind of a throwaway function that you're not going to want to use again. So this kind of cuts against the main arguments for using functions, which are reusability and clarity. You're not reusing this because you're throwing it away. But in many cases, you just need to be passing a function to some other function. sapply expects a function. And so we need to give it a function. And in this case, we're going to use a very simple function, x times 3. All right, so this is one of the cases where this is not the right thing to do. And instead, of course, you should just multiply your random normals by 3 explicitly. And of course, the point here, we've kind of been applying, and maybe Chris said this explicitly, functions, just like all of your other pieces of data, are an object. Okay, so they can be an object, and then more specifically, they can be a string or a numeric variable or a list or a vector or a data frame. But everything is an object, and that means that everything can be passed in and used in kind of the same way. So sapply is a function, and it takes a function as an argument, and you can do that because a function is just an object that you can throw around. All right. All right, and then this is the last thing I wanted to talk about. So, so these are some words up here, and I think I'm going to skip the words really quick, and we're just going to play a little. We're going to do a little puzzle. Okay, so let's take a look at this code, and let's make it a little bit larger so you can see what's going on. All right, so we've defined a variable a. We set it equal to 1. We've defined a variable b and set that equal to 2. Okay, so a is 1, b is 2. All right, now we define a function that we're going to call f. It takes an argument x. If that x is equal to the character a, this function is going to return the value of a. Otherwise, if it's equal to a character b, it's going to return the value of b. If it's not equal to either of those, nothing happens. This function doesn't return anything. Okay, so notice, by the way, I'm not using the explicit return. I could have written this as return. There's letters all over the place. Could have written this as return a. Instead, I'm using this implicit last thing that's evaluated in the function. Okay, so this is f. It returns the value of a or b depending on what you ask for the value of. Okay, now we have g. Inside g is a function that takes an argument x. We're going to set a equal to 2, and we're going to set b equal to 1. And so what you'll notice is that we're switching the positions of, we're switching the values that are in a and in b, and then we're going to call the function x. And so the question of scoping is basically when f gets evaluated, what does it see is the value of a, and what does it see as the value of b? And this is a choice that programming languages can make. They can, many programming languages sort of do this in different ways. So it turns out that the way that R does it is what's called lexical scoping, which is kind of jargon. What that means is that functions can access variables. They access variables relative to where the function is defined, not relative to where it is called. Okay? So we've set a equals to 2 and b equals to 1 inside g, and then we've called f of x. Okay? But what f of a is going to return, the a value that it's going to return, is whatever a value it saw when it was defined, when the function f was defined. And it was defined up here. It wasn't defined in here. It was defined up here. And so what that means is that the value of a that f is going to see and is going to return is 1. Okay? So that's what's meant by lexical scoping. You can look at where the function is defined, and you can figure out what a is going to be by just looking, upstream in the code from there. All right, so if we evaluate this, this block of code, what we'll find is that g of a indeed returns 1, okay? Because f is giving us the value of a that was defined relative to, that it was equal to at the time f was defined.
So what are the definitions of a and b inside of the function g doing anything?
They don't do anything that is obvious. I mean, those values get set inside the function and then they get thrown away. Okay, and so that's actually another question of scoping. Okay, and so what you can see here is I'm printing out a as well. So what is a equal to now after g has been evaluated? And it turns out that what a is equal to is still 1. A is equal to 1 on the outside. A was set equal to 2 in the context of running g, but that was in an inner scope. Okay, so you can play around with that variable in the inner scope, and the outer scope, which is the main body of the outer function, the value of a does not change in that outer scope. Okay, so there's sort of two things that are going on here. There's this question of lexical scoping. The variables are set based on where the functions are defined, and then number 2 is this question of like inner versus outer scope, or more generically like global scope versus various inner local scopes. Okay, and so the value of a that we can access, even though we've run g and a was set equal to 2 inside g, back inside the outer scope, back inside the main body of the function, the value of a was not changed. Okay, so this is kind of a fine point, but it will be relevant when you're defining functions, defining and using functions.
If we set a to 2 and b to 1 inside the f function, would it return 2?
Yeah, it would return 2, but so let's do as he suggests. Set a equal to 2 and b equal to 1 inside there. So the evaluation of g will return 2. I'm almost positive. Hope I'm not wrong. Right, so g still returns 2, but the evaluation of a right here on the outside still returns 1. So we changed a and b inside both of these functions, but we don't see that on the outer scope. You can't change external variables from within a function. You can access their values, but you can't actually change the external values.
Is there a way you can force it to have like global variables?
Yeah, there are ways that you can set global variables, and I'm not going to be able to tell you what they are off the top of my head, but it's going to be something like an external namespace. You're going to access some external namespace and explicitly say that you want to set the global version equal to 1. Which you could do, but in general, really, kind of the flow of the code should be that functions return values that you want to be used, and they don't kind of muck up the variables that are in the rest of the code.
Yeah, there are a couple principles here. One of which is that in general, it's a good idea not to have a lot of global variables that you're referencing within your function. So you should be having any variables that are used to reference within a function. You should try and have those just be variables that are either defined in the function or passed into the function, as opposed to being variables that are outside the function in the global workspace. And the other thing, and this is a principle,
and that's one way. One important reason for that is so your functions can be modular, so that you can use them in one file or you can use them in another file, and the same thing will happen every time. It doesn't sort of depend on which file you're running it from.
And the other principle here is that what R does is, unlike some other languages, and I mentioned this briefly before, when you pass in arguments to a function, and if you modify the input arguments to the function, those modifications are not going to be seen outside the function when the function is done. And this is basically pass by reference versus pass by value. That R passes things by value. Essentially it makes a copy within the function, and then it's working with the copy that's sitting in the function. And then unless you return the modified result back out of the function, your changes disappear as soon as the function ends. And so if I say x is 3, and then I say some function f applied to x, and I do some stuff with with the argument x in the function, it's not going to change the original x that's outside the function in the global workspace. And the reason the R developers chose to do it that way was this principle of modularity that a function should not sort of do things behind the scenes and change things without you being aware of it. And it forces you to be aware of things by.
That was nice work.
It forces you to be aware of changes that a function makes by forcing you to pass the resulting change out of the function. You have a really accurate arm.
Nice catch. Okay, so that was pretty light. A few breakout problems. So about 20 minutes on that. Then we'll probably 20 minutes or so, and then look at solutions. Sound good?
Yep.
Okay. All right. So there you go. All right, guys, I'm going to talk really quickly about the solutions to those various breakout problems. Okay, so the first one was write a function that returns the mean of n randomly distributed normal numbers. Okay, so what we do is we define a function. We can call it whatever we want. Usually it's better to call it something that is clear what it's going to do. So I'm going to call it mean of normals. It's a function that takes an argument in. This argument is going to be the number of random normals we want to generate. And then whatever that happens between these braces is going to get evaluated. Okay, and so what I'm doing here is I'm taking the mean of in random normal values and returning that. Right? So here again, I'm not using that explicit return statement. I'm using the fact that this is the only line in this function. And so that's going to be the thing that gets returned. So if we evaluate that whole chunk, what we see is first the function gets defined up here, and then the mean of normals for 1, 10, 100, 1,000, and 10,000. And what we see is, more or less, as you would expect, this average gets closer to 0 as the number of random variables that you're generating becomes large. Okay, so that was a pretty quick one-liner and not really worth defining a function for. Okay, so breakout problem number 2 was just an extension of number 1. So in this case, what we want to do is allow the user to pass the mean and the standard deviation parameters for the normal distribution. Okay, and so what I'm doing here is I'm setting mean and standard deviation. I'm giving them default values of 0 and 1, which are just the default values that they would have already in the rnorm function. And I do the same thing. I generate this list of in random normals. And then, because what I want to return is both the mean and the median here, in general, you just return one thing. But because this is R, that one thing is an object, and that object can be whatever we want it to be. Okay, so in order to return two things, in order to return the mean and the median, I'm going to create a list object that has the mean of these variables and the median of these variables. And then just so it's kind of useful for the end user, I'm going to give names to those elements in the list. I'm going to name them mean, and I'm going to name them median, and then I'm going to return this, this object called out on the last line.
So this is still going to be, wait, oh, never mind. Sorry.
Okay, no problem. So I called this function stats of normals, so I'm calling it with 1, with a mean of 5, and a standard deviation of 2, and so you can see on that function call, it returned this returns 6.9. Okay, so that's kind of a number that we would expect. The mean and the median are the same because there's just one number. And then the same thing happened down here. For 10,000 random normals, the mean is indeed very close to the mean that we told it, and the median is as well. There's a slightly different way that we could have written this. Okay, so the way that we wrote this was to explicitly have these functions mean and standard deviation and explicitly pass them through to the R norm. But I believe what we could have done instead is to use this ellipsis argument and just say that all of those ellipsis arguments are going to get passed straight on through to R norm. And I'm crossing my fingers. Maybe this will work. Yeah, so it indeed appears to have worked. So the mean and median parameters that we sent straight through to R norm were interpreted appropriately as the mean and the median. And just to be clear, we could sort of add that in here. We could say not mean and median, mean and standard deviation. So we could have explicitly said this one is the mean, this one's the standard deviation, pass them on through to the R norm function. Okay, so that's number 2. That demonstrates using default values, and I guess I've demonstrated this ellipsis thing. And it also demonstrates returning something that's more complicated than just a number. You can return whatever you want, a list or vector or whatever. In many cases, when you start doing sort of complicated statistical programming, something that you frequently want to return a function, kind of like write a function in code inside a function and return that function. So then you can call it later on. That's kind of, it's called like a function generator. This wouldn't be something you'd do in the context of a normal statistical analysis, though. Okay, and then problem number 3, write a function that repeatedly generates random normal variables until it generates one that's more than n standard deviations from the mean. So this one's kind of dangerous. If you pass it a large n, like say 5 standard deviations from the mean, that's going to take a very long time to randomly generate numbers and find one that's more than 5 standard deviations from the mean. So this is kind of a silly function. But I'm going to define it anyway, call it n until fluctuation. Here, what n is representing is the standard deviation above which is our threshold, above which we want to generate a random normal. Okay, and here we're going to use a while loop to do this. We're going to keep generating random normal variables, and once one of them goes above sigma, greater than or equal to whatever is passed as sigma, the loop will stop, the while loop will stop, and we'll return I, which is just sort of a counter for how many times we've gone through this loop. Okay, so we initialized our counter to 0, and then each time through we incremented it by 1. So we could keep track of how far we were in the loop. Okay, so let's define it. And if you run it for 1 standard deviation, it doesn't take very long. There it just took 2 coin flips before it found one that was more than 1 standard deviation from the mean. But these other ones, 2, 3, and 4 standard deviations, you'll notice that it took 23,000 random numbers generated before it found one that was more than 4 standard deviations from the mean. So this is kind of, again, what we expect for a Gaussian. And that's it. Any questions about that? Went over it pretty quick, but these solutions will be online after the bootcamp. Say that again?
The R norm 1.
Uh-huh.
The 1 is like for?
The 1 is to generate 1 random normal value. Because each time through the loop, we're just generating 1 random number.
I got the problem.
Yeah, we could have done this by generating a whole list of random numbers and then going through the list and see how far we get through the list before we find one that's a fluctuation. So that would have worked as well. All right, I guess we're moving on to Chris. Get you open here. We do, but it sucks. It's this guy. Mm-hmm. All right. So there's your RMD. Your namespace is still polluted.
Well, yeah, it really is. All right. Okay. Hey, everybody. My name's Chris. To make things a little bit more confusing for y'all, I'm third year now in the political science department. And my job now with this module, sort of to make you guys realize that what you've been doing for the last 6 hours is actually worth something, is to show you some cool, useful stuff that R can do. So that's why the module title here is useful stuff. Yeah. So here's the basic idea, right? You've got all these pieces now. You can sort of do some simple things in R. You can use it as a calculator. You can define some functions, merge, subset, plot, all that sort of thing, which is cool. But, a lot of you aren't completely, computer illiterate, and if you had to do these things, you could say use a calculator, or Excel, or unfortunately Stata. But one of the really good things about R is that it does all these things, but it does it in a way that has a very sort of simple syntax, which also allows you to apply those sorts of same syntaxes to more complicated problems. So even though all you really know how to do right now is relatively simple, using those basic tools that you've got at this point, you can do some really complicated things with not too much additional work. So, yeah, this is all about that, basically doing useful stuff. So this is the useful stuff module. So obviously it's abridged. There's lots of things that R can do that's very useful. But for the next, I guess, 40 minutes or so, we'll see how long this takes, I'm going to go over 3 particularly useful things, especially for people who aren't so much interested in sort of the, yeah. My battery's going to die. All right. Okay. So now that we will actually make it through this, let's continue. So I'm basically today going to cover 3 broad areas that people who work more in applied problems are going to really need to do on a daily basis. And then tomorrow I'm also going to go over some things related to graphics, which are pretty fun. So what we're going to be doing is going over stratified analyses and groupwise operations. You saw a little bit on how to do that already, but I'm going to be introducing you to a new package, a relatively new package called plier, which sort of takes the very complicated massive applies and other functions for doing groupwise operations that you've seen already and sort of puts it into one very simple logic, which is actually very helpful for doing things, for doing groupwise operations simply and cleanly, and also fast. We're going to go over a bit on data manipulation, changing your data sets from wide to long, recasting data sets, melting data sets, that sort of thing. And we're going to go a little bit further into the regression element. Chris has already gone over the LM package, or the LM function. I'm going to show you a little bit about GLM, which is the Generalized Linear Model package. And I'm also going to go into a little bit about how you would do the sorts of things in Stata that would require, for instance, just ticking a box like, please cluster my standard errors. It's a little bit more difficult in R, but I want to be able to give you guys the tools to do those sorts of things should you want to actually do them in R. And again, the graphics we'll get tomorrow, so I'll tell you more about that tomorrow. So just to give you a little bit of background on this data set that we've been dealing with, I'm a political scientist, so I was very disturbed that when it came to the voting preference data, I could only get, oh, this person voted for 1, or this person voted for 2. So I wanted to actually track down what we were actually dealing with here, which sort of brings me to a different note. I found a data set that actually has some metadata on this. It's the same data set, except it says, oh, this number 1 is actually Kerry, 2 is actually Bush. 3, interestingly enough, is Ralph Nader, just in case you were wondering. So if any of your code doesn't really work, let us know, and we'll give you a better data set that actually works with those data labels. So this is taken from a paper by Andrew Gelman, related to his red state, blue state stuff. You can read more about this if you want, but just so you have an idea what we're actually going to be trying to work with today. So we've got this data set now, right? Imagine you are some sort of new graduate student. You've got to write some paper, and you've got this cool data set, and you want to say, all right, first step, I want to have an idea of what's actually going on in my data set. A really easy thing to do, which you may have seen already, is to just take a look at the structure. And you can see here in this data set, it's a data frame, and it's got all these different variables right here. We know what kind of classes they are. As you can see, there's a whole ton of factors, which is going to make our life a little bit more difficult. But as Chris said previously, sometimes this is just how these data sets end up getting read into R. But it's good before we actually go into any of things, especially like regression, to know exactly what we're going to be dealing with here in terms of the type of variables. So we see we've got a couple of different things we can take a look at. We have the state, we have the presidential voting preference, we have gender, race, sort of a binned age variable, as well as party ID, income, and lots of other cool things there. So if you've got this data, and now we basically know what's in it,
your first step probably is going to say, well, I'd like to get some summary statistics on these things. And in lots of other statistical packages, you know, this comes up as a table function, or there might even be some button on a graphical interface that you would use. In R, not always the easiest thing to do, but we'll sort of go through a couple of attempts to do it here and show you how it can get very complicated very quickly, but then we'll also give you some tools that will help you do this in a very easy way. So I should just note, for those of you that are actually worried about the interpretation of these variables that we're going to be working with, age and income, for instance, they're binned, and the bins are of unequal width. So I'm going to be doing some things with them that if I was actually going to try and do some analysis would be terrible to do, and you should never do them. But for sort of ease of demonstration here, we're just going to go with it and pretend that the bins are actually equal width, and we can do some of these transformations that I'm going to do.
So Chris, is the data file that you're reading in that has the information about that a 1 is carry and 2 is push and whatnot, you're reading in a different data file than I was reading in, is that right?
I think I may have when I wrote it, but I just ran it on my machine and it seemed to work okay. So it's the same exact file, except now I told Stata to say, instead of putting 1, 2, 3, 4, 5, it says carry, bush, nadir, other, that sort of thing.
So instead of the numeric labeling, it has actual.
Exactly. Exactly, yeah. But if it doesn't work for anyone, let us know and we can accommodate you in some way.
The data file that you guys still have access to is still the one that I have that has the 1s, the 2s, the 3s instead of the bush, the carry.
Right. Exactly. Okay. So maybe a good place to start is to try and figure out some very basic sample statistics about age, for instance. Now, I'm not sure if Chris talked about this, but a good way if you want to get an idea of the range of each one of your variables is to just use this command unique. Right here, we're applying it to basically a vector that we're pulling out of our data frame, my data, H9. You can see here, it's a factor. We've got these levels here, and these are the unique values in the particular data set. We do have a missing value, too, that's going to be unique. This looks a little weird. I don't know what exactly this was supposed to be, but I think the compiler came out weird on this slide. Anyway, ignore this for now. So say we wanted to calculate the mean, for instance, standard deviation, that sort of thing. We can do this by ways you guys have already seen, right? We have to convert this data to as numeric in the first place to get away from this, this factor issue. What R is going to do is actually it's going to be able to sort out a general ordering of these variables, and then it will just assign some sort of placeholder like 1, 2, 3, 4. So you can get this idea here. In terms of R's binning, it says the average age is about 4.5. If you look back and see when you convert the age, the uniques in the age variable, when you look back to see what number it actually assigns, this ends up being around the 40 to 44 range. Obviously, when you have data that's not as a factor and you actually have continuous data, you wouldn't have to jump through these hoops by putting them in as numeric. But for the data set that we're working with now, this is just an example statistic that we could get. You can also do the same thing with the standard deviation. Again, the function is very simple, SD. It requires the exact same input command on the X, removing the missing variables. Again, it's the same sort of R-interpreted age. You can do that for the median as well. And there's also a nifty little function if you wanted to see what the various ages were at the different sort of quantiles within your data set. You can use the quantile function. Again, you put in the vector that you want R to work over. Again, this is our as numeric age vector. You have you're taking out the missing values here, and what you see here is it's sort of goes off the page here a little bit, but you need to put in basically the different quantile the different percentage levels that you want R to actually calculate. So for this case, we have a sequence going from 0 to 1, and it's going by 0.2. So we're basically going to have the distribution of quintiles. So these are some pretty basic statistics that we might want to do just when we're just getting started with a data set. And just to give another example here, we could do the same thing with income. You look at the unique data, the unique values. Again, we see that it's binned at these various income levels. And again, it's a factor. It's got these other levels here. Again, ignore this thing. This was some formatting that didn't work out on this slide. But we can do the same thing here. apply the mean to the as numeric of income, removing the values that are missing. We can apply the standard deviation, the median, the quantile, all these sorts of things.
It does look like in this case like it's not even, the categories are not even ordered in their natural ordering. So just a warning that taking the mean of those values doesn't make a lot of sense here.
Yeah, I mean, that's why I said if you were actually doing this for your own purposes of actually writing a paper or something like that, you would want to come up with better measurements. But I just wanted to introduce you guys to these mean and standard deviation and quantile functions, just so you can get an idea of things you might do when you start analyzing a data set. But there are some other things that you can do that sometimes require a little bit of hoop jumping in R. For instance, if we wanted to get some frequency data, a very common technique that we'll use is to actually work with the length of our different variables. So for instance, if I wanted to get an idea of the gender balance in this data, right? One thing I could do is figure out the length of a particular vector such that the values of that vector were equal to one thing like, say, male or female. So I basically have a count of how many males or females there are. And then I can divide that by the length of the entire vector. You can see that right here. I'm just taking the length of this particular, the sect variable that I pulled out. And I'm just selecting those particular ones that are equal to male, and I'm dividing it by the length of the entire vector. And for those of you that are wondering, if you haven't seen this already, this little cat function here, this is the same idea as print. What it avoids basically though is putting that little numerical 1 out there. Same basic idea. So you can see in our data set here, we've got about 45% were male, and we can do the same exact thing, just take out the male here, put in female here, and you can see that it's 54.87%. So, and again, same idea. You could also do it for political balance if you wanted to get an idea of, okay, how many Republicans, what percentage of Republicans, what percentage of Democrats do I have in my data, that sort of thing. You can do it for Democrats here, Republicans here, independents. The syntax is exactly the same. All you're changing is basically the overall vector that you're trying to work with, basically which column in your data frame, and the party ID that you're interested in for determining some sort of frequency. And we could do the same thing for racial balance as well. These are just some examples to let you guys see how you would actually do this in practice. But you can imagine, right, if you wanted to do, if you wanted to figure out if you wanted to summarize your data set on the basis of variables that had, say, a longer number of unique values, or if you wanted to summarize your data set in terms of variables, in terms of more than one variable, or 2 or 3 or 4 or 5, coming up with your summary statistics that way is going to take a long time, and it could be really painful to do if you wanted to do them in the way we just did. You can see the example here. Suppose we wanted to know how voting behavior in the 2004 presidential election varied by race. That means you'd have to do all of those frequencies for all the unique values in race, and you'd have to calculate the vote choice for each one of Bush, Kerry, or Nader, or other or no vote. And obviously this can take a long time, and as Chris mentioned, the more you actually have to write out, the chances that you're going to make some sort of error, they tend to increase pretty fast. So, this looks kind of bad in this particular one here. I'll post a better version of these slides. All this stuff it was written for a different compiler that actually made this look like a nice table. So I'm going to have to give you the verbal explanation then. So everyone pay attention here very closely. All of these techniques that we're going to be showing you rely on this idea called the split, apply, combine strategy. And the basic idea is if I want to do some sort of group-wise operation on my data set, if I want to know how summary statistics change according to groupings of X number of variables that have Y number of unique values, what I need to do is 3 things. First thing I need to do is I need to take my data and I need to split it up on the basis of some variable. So I'm basically going to take this one variable and I'm going to say, all right, all these rows or all these columns that I'm interested in, however I'm going to split it up, that have one particular value on my splitting variable, I'm going to take them and I'm going to just put them in different categories, right? I'm going to separate them completely. I'm going to go back in, and to each one of these new smaller data sets that I've made, I'm going to apply some sort of function that in some way manipulates the data that I'm working with or creates a new tiny data set, whatever I want to do to it. And the last section of this is the combine thing, where now that I've got all these new data sets, I've got to figure out some way to piece these back together. So there's a couple of different ways that you can do this. And everything basically relies upon the same strategy. It's just how complicated it actually ends up being. So I'm going to show you, just for demonstration purposes, the first way, and this is definitely the hardest way, and definitely the way you should never, ever do it again, save for right now to figure out how it actually works. So for our question above, we wanted to know how voting preference changed over the different races, right? So the first thing I would do is I need to split this data up somehow. So what I'm going to do is I'm going to make a subset that just has white voters in it. I'm going to make a subset that just has black voters in it. And I'm going to make a subset that just has Hispanic voters in it. And the way you can do that, the syntax for that is right here. I don't know if you guys have seen the which function yet, but if you like to subset your data using brackets, which is a convenient way to put a whole lot of conditions in either one of your row or one of your column selectors. So you can see what we have here. We're selecting those particular rows that have white as the race, and those particular rows for which race is not missing. So we've got a non-missing subset of white voters from our overall data set. And we applied the same exact thing for black. Same.
Just to point out, this is not to be overly critical, but that's a little bit redundant because you've got the which wrapped around a vector of trues and falses, and you can just directly use the trues and falses.
Right. You can do that too, yeah.
So you don't actually need the which, but it doesn't hurt to have it anyway.
Many ways to do the same thing. So yeah, so I've got these 3 different data sets right now. I've split them up. That's the first stage. Now what I need to do is I need to apply whatever function I'm interested in. And remember, what we're interested in now is coming up with these voting percentages, right? So those things we did before, where we actually tallied up the different vote counts, we need to do the same thing, except we need to apply them to each of our new data sets. So what we're doing here is we're basically taking our white data sets, and I'm going to calculate a statistic, which is the same percentage that we saw before, of white voters that voted for Kerry, white voters that voted for Bush, for Nader, and for other. I need to do that for all the black the black data set, all these various permutations. And again, you get a whole boatload of things here. I obviously didn't go through it because it would take a long time. And then once you've got these new objects here, you need to somehow combine them. And since we basically combined them since we generated them in an extremely basic way, I basically just took them and put them into a data frame here with some identifiers for the columns. So that was actually a very long and a very painful way to do it. It was extremely painful to write. It pained me to actually do it. So you're never going to have to do this again. But before I get to the real good way, I'm going to show you one more way that you could do it, which is a little bit more sophisticated. It's another split, apply, combine strategy that people use pretty frequently. Again, here what we do when we split the data, we can use the split function, which Chris talked about earlier this morning. We're splitting this particular vector right here, and we're going to split it on the basis of race. And that's going to give us a list of different little data frames that are uniform on race for each element of the list. And then what we're going to do here is we're basically going to apply this. We're going to make a matrix basically to house our results. You can see this right here. It's all ready to go. We've got our missing values, and then very unfortunately, of course, I'm going to use a for loop here to fill in these results. And again, this is the same exact statistic that we were calculating before. All this function is doing is saying, okay, for this individual row, in this case, which is going to be our race, you need to calculate the Kerry percentage, the Bush percentage, the Nader percentage, and the other percentage, and put it in the appropriate cell of this matrix here. And you can see once you run that, it ends up in the matrix down here with all our results filled in. All right, so now we've got sort of the junky ways to do this out of the way. So this is tabulating the easy way. And it might not look easy right now, but on the next slide I'll show you the basic syntax, and it's going to be pretty easy. So this line up here, all I'm doing basically just to make my life a little bit easier is to limit my data, again, I suppose, redundantly perhaps. I'm just limiting my data to that which is not missing, and I'm limiting myself to only 4 candidates here that I'm interested in, and of course the things that aren't missing. And what I'm doing here is I'm applying this magical function called ddply to my data. It's going to split up the data on the basis of the variable. Okay, this thing broke. Oh, there it is. On the basis of the variables, of the different values on the variable race. I'm going to put in this function that I want to apply, which is called summarize, which we'll go over in a second. And then I want to create these different columns, which you can see, you'll recognize, are all the same statistic that we've been calculating in the previous examples. And in just this, 3 total lines for this, although albeit one bigger one here, we get the exact same result in a nice little table. So this function ddply right here. This is one function that comes in a bigger package of functions like this called plier. It's written by a guy named Hadley Wickham, who's a professor of statistics at Rice. And this is really, it's sort of your go-to package for every split, apply, combine thing that you'd want to do. I guess probably the motivation for the package's development is related to an issue that Chris talked about before, which is when you want to go to some sort of apply function that's in the basic R software, it can be a little daunting, whether you pick sapply, tapply, vapply, regular apply, or lapply, and then when you actually try and work with those functions, the particular arguments that they take are not uniform. Sometimes you'll have to specify a margin, other times you won't. Some different applies will take different functions that are unique to them. But what ddply does is it basically takes one standard, I should say this is what plier does, it takes one standard way of inputting data and basically applies a whole lot of maneuverability over different object types, and it's all standardized. But there's a couple of other advantages that I think it'll become more clear after Jared's section tomorrow, for instance, why these are such great things. But so as I said, you don't have to worry about different names or different argument types or output consistencies. It's very easily parallelized if you have to, do vector operations over very, very big data sets that can take a long time. The other really great thing is if you have to do something that takes a really, really long time, it has an option to print out progress bars so you can see how far along it actually is. You don't have to write your own informative progress bar into your function. And the other really great thing is it gives you informative error messages. So if you're trying to apply something over a very large data set, and if you're using sapply or one of the base R functions, it's probably not going to tell you very clearly what happened if something did go wrong. But most of the plier functions actually have something really nice that's built in to tell you actually what the issue is. So maybe a downside at first is when you open up the plier package, if you thought there were a lot of applied functions in the base R software, you might be a little bit scared by the 30 or so different apply functions that come with the plier package. But there's a very sort of simple nomenclature which actually makes it a whole lot easier to understand and makes it a whole lot easier to get to the actual function that you're looking for. So there's 2 basic questions which helps you navigate throughout the many functions in this package. The first one is, what's the class of your input object? Basically, are you putting in a data frame? Are you putting in a list? Something like that. And what do you want, once you've done your split, your apply, and your combine, what would you like that final combined element to be? Would you like it to be a data frame or a list, et cetera, et cetera? And what's critical is sort of the first letter of all of those things. If you want to be a data frame, if you're putting in a data frame and you want to return the results as a data frame, you're going to need to use ddply. If you wanted to put in a data frame and return your results as a list, you'll use a function called dlply. So that's the basic idea for selecting which function you actually want to use. So there's a very basic syntax here for calling all of these functions. You see whatever ply you want to use. The data command, as well as the variable command and the function command, just note they're all preceded by a period here, which I believe it's because of it's basically to make the internal parts of the function actually work. You can't just have data without the period there. That will make things sort of go bust. But all you have to do is enter the data set that you're interested in. You put that right here. The variables that you're interested in, these are basically the variables, the values of which you want to split the data apart with. So if I want to split on race and gender and say party affiliation, all I would do inside this, this parentheses here is put race and gender and political affiliation, et cetera, et cetera. These three dots here are actual ellipses. They're not the type of functional ellipses that Jacob was talking about last module. And then you just specify the function that you're most interested, that you want to apply to each one of these newly created objects, newly subsetted objects. So if you consider our previous example, you can see the direct analog here. In our object vote by race, we're calling on ddply, which means we have some sort of data frame. We want it to be split up according to race in this case. And after it's split up into race, we want to apply this function summarize, which I'll tell you about in just a sec. And for each, in that new data set, the functions that we want to apply, we basically want to calculate the percentage of individuals that voted for Kerry, for Bush, for Nader, and for other. Now, I've told you about summarize twice now without actually telling you what it is. So now's the time to do it. Summarize is a function that basically what it says is, I like this data set, it's really cool, but I want you to give me a brand new data set which is comprised of just these things that the function that you specify would actually put out. So we're feeding in this big whole data set that's got variables on race, gender, political affiliation, all that sort of thing. But when we put summarize out here, all it's basically going to return is the values of the return values of these functions that you specify over here on the side. Yeah, so that's why we're calling ddply. And again, this object that it's going to create with columns for Kerry and Bush and Nader and other, it's going to return that as a data frame. Is there a question? Yeah?
Yeah. To do more than one of those, usually what I end up doing, like for instance, if you want the mean and then the standard deviation, you have to type in those, just like you did here, but then if you wanted another thing, you'd have to retype everything in and say mean before it. Is there a way to just have multiple functions, so if you want a mean, standard deviation, and the proportion all in one table, how to do that really quickly without having to retype all those variables and functions within the ddply?
So at some point, you're going to have to type all those functions in. Whether or not you type them, separated by a whole bunch of commas here, that's a different question. You could write your own personal function which says, okay, once I've got this object, I want you to always calculate the mean, standard deviation, all these percentages, that sort of thing, and spit these all back out for me. You could certainly do that. But it's just, this is just a quick way that I wrote it up here like that. Does that make sense?
Yeah.
Okay. So the cool thing about this sort of syntax here, right, is it makes it really easy. It makes it really easy to scale up. So the idea here is, right, if I just splitting it by race, we saw that it was complicated to do by hand, but we could probably do it. We could split our data frame up in this case into a whole bunch of different comparisons, really just by adding different variables in there: race, political identification, income, age, all that sort of thing. And the syntax, you'll see here, it doesn't really change too much when you go across different apply functions. So for instance, this is using the plier function dlply. Again, we're taking in a data frame, we're splitting, applying, and applying some function, and we're going to combine the results, and what we're going to get is a list. Okay? So you see here again, dlply, we're putting in the clean data set. The variables we want to split are really just on race. We're applying this summarize function, and we want to calculate the percentages for all these voting strategies here. And this is our output. We're going to get a list, one list for just the white voters, for the black voters, Hispanic, Latino, Asian, and let's see here, other. Yeah. And now say I didn't want to do this in terms of a list. Say I started with a list, but I want to do a split and an apply for each element of this list, and then I want to combine it into a data frame. Literally all you do is take your list right here, you apply ldply. Again, your data in this case is going to be the races here. We've split this up. This comes from the second it comes from the second hard way of tabulating. It's going to apply the same function here, basically with summarize, and then it gives you all the percentages for the different candidates. And again here, it's going from this list right here that we split and giving us a data frame with the voting results that we were interested in. Same thing here. This is probably getting redundant at this point, but just so you see it, with ll-ply, we could take that list, calculate the statistics we were interested in, and again, spit out a list. So you guys can see that there. So there's a lot of different functions that are very commonly used, especially if you want to do summary statistics or really basic things with these various plier functions. You saw summarize. Another one is transform. So transform and mutate, what they do essentially is instead of taking in some sort of object and then returning eventually a completely new object, transform and mutate allow you to take that object and change it in some fashion, like add a column, for instance, add a whole bunch of columns, alter currently existing rows or columns, and then take that altered data set and return it directly to you here. But again, it's the same idea. So say we wanted to basically create an indicator variable of some sort for old people. In this case, it would be, we'll say, all right, if you're over 65, we'll count you as old, and we may just want to indicate that for some reason. So, you never know. We're calling ddply because this is a data frame. We'd like to keep it as a data frame. The data set that we're applying it to is this clean data. The variable that we're gonna be splitting it here is by race, and we're going to be transforming it. The split doesn't really matter too much in this case. This actually should not be here, but that's all right. We're transforming it, and we're creating this new variable, which is called old, and we're just applying the if-else function. And if you're 65 or over, according to the age variable here, we're going to put 1, otherwise 0, and then this is just the printed result. You can see here, this one, old guy here, he's got the indicator here on 1, as well as this guy down here. That's just the first 100 rows or so. So you might be thinking to yourself, well, this is great. I can really speed up this process super fast by just throwing in a whole bunch of new columns that I would add to my data frame. And I can generate one column, and then I can take the value in that column and turn it into a value for another column. You can't do that with a call to transform. To do that, you have to use a function called mutate. And this basically what it allows you to do in a single line with various plier functions to say, all right, I want to create this old data set, and then based upon whether or not you are old in this indicator for whatever reason, say then I want to classify you as an old man. It'll take that value. You can apply some sort of function to that new old column that you've created, and then you can work some sort of function on it. Here again, it's applying this old man function here. So if you're old and you're male, we're going to indicate that as 1. If not, we're going to give you 0. And you can see way down here, see the older female here has a 1 in our original old column, and the old man has a 1 here for being an old man. So that's transform. Some other functions that you might want to use that are really helpful for doing things with plier and data frames in particular is arrange. And this is basically just a function that allows you to order the rows in the data frame by however many variables in however way you want to. So I'm taking a snippet of this data here, which is the first 50 rows of our old men data, and these particular columns for gender, race, age, and whether they're old and whether they're an old man. So you can see this here. This is basically the code that we get. And what I want to do now is I want to take this little snippet of data here, and I want to arrange it first in terms of gender, and then I also want to arrange it in terms of their overall age. But for the however you want to define this, it's weird to sort of think about ascending and descending of categorical variables, but it'll pick one to just put it first. And so for this case, we'll say just order it somehow in terms of gender, but then we've got this age variable here, and R can coerce it into something that's vaguely recognized as being ordered, so we want it to be sort of a descending sort. And then so if you compare this data set that we have up here, it's clearly not ordered in terms of gender, just because we only took a small snippet, it's obviously still white, but it's not ordered in terms of age or in terms of the indicator variables that we defined. However, after we apply this arrange function right here, you can see we've got all males first, and then we've got the old folks here. Basically, we've got the higher coerced ages are coming higher in our data than the lower coerced ages. So this is the arrange function. Very, very helpful for ordering data frames. You could see we could do it in the opposite way here. Just another example. This time, instead of ordering it in terms of age and then ordering in terms of gender, which again, this is just sort of meaningless, but you can apply it and R will interpret it in some way. It's ordering first in terms of the gender and then in terms of the age. So this is the arrange function. Obviously, you can, it's pretty easy, and you can change it around however you like. And the last note on functions, just sometimes when you start working with plier to try and actually, do things in real data, it's a little bit difficult to think about if you're calling a specific, if you're defining your own function, for instance, function x and blah, whatever you want to do. Just remember that basically what the plier functions are going to give you is sort of a subset of whatever you put in. If you put in a big data frame and you just call that particular subset of the data frame, just know when you're writing your function, however you're going to write it, it's going to be applied to that small data frame. And this is just, I remember when I was learning R, this was a sort of weird thing to think about. What is it actually working with when I'm saying apply these things to a particular, to these subsets? So just a thing to remember is that it's going to be calling these exact subsets, and this will be relevant for your breakout thing in a minute. So think in terms of whatever it is you originally put in to your function. Okay. So that's sort of the plier package. Again, it's really, really simple. That's why I can go through it in a very short amount of time. And it's very easy to use, and it's really well documented. So it shouldn't be too much of a problem for you guys to get up and running with that. But this is sort of the second very useful task that I think R is pretty adept at. And I don't know if this happens to people who do mostly things like statistics or the natural sciences, but if you're a social scientist and you want to go get some big data set from the World Bank or the IMF or something like that, and you download this from the website, and you don't really know what you're getting, but there's probably a pretty good chance that it's going to look like this. And all you wanted to do was just put like a time series graph up there, but the things, they're in columns like this, and the countries are down here, and sometimes this can be really annoying to have to try and coerce in some way to get it such that you could basically just isolate these particular years right here. You could put it into a column and then very easily feed it into some sort of graphing program. So the same guy who made this whole plier package also made another package which will make your life easy called reshape2, which is basically takes a data set of some sort like this and it coerces it in a way that you'd like. So again, the idea here is that R does have built-in ways to do these sort of object transformations, and we've seen a bunch of them already, including aggregate and by, t-apply, etc. But when you actually get into the nitty-gritty, the arguments that these functions are going to take are not really consistent as you move across the functions, and they're not parallelizable, all these sorts of things. Reshape is basically trying to overcome this problem. And the syntax is actually extremely, extremely simple. I mean, it's kind of basic, truth be told. And so there's two basic functions within this reshape package that you really need to worry about. One is melt, and one is cast. And so you have to sort of think about what the guy who wrote this was thinking of. He wants to take this data set that is sort of cast some way as you get it. He wants to take the columns and the rows and melt them down to some sort of basic level that you can deal with. For instance, in the example that I had up here before, we might want to take all of these columns here and collapse them into maybe one column that's an indicator of whatever this variable is, and then have one column for values. That's the idea of melting this object, right? And sort of the complete reverse of that is if you have this melted object, you might want to cast it. I don't know exactly why you would want to, but maybe once you had this melted data set, you would want to put it right back to where it was. Maybe you messed up the first time or something like that. but it has this cast function as well. So I just want to show you basically how you would work with both of these functions. So this is the melt function in reshape 2. And the basic idea is you have to take your data frame. It works mostly, I think it works exclusively on data frame, so I'm just going to go with that. You take your data frame and you need to melt it into sort of 3 essential components that you need to worry about. The first thing is case identifiers. So this is basically one way that you would want to distinguish all the different rows in your data frame. And this could be, for instance, in our previous example, it could be a country and it could be a year, or something like that. It's got to be something that's basically going to establish more or less a consistent column identifier for your variables. The second thing you want to identify are characteristic variables, and these are sort of the variables that you're interested in sort of melting in some way. You want to take them and you basically want to collapse them or alter them in some way. They're the things that you're not really too worried about in terms of being case identifiers. And the last thing, obviously, is the variable values for all of these examples. So, for instance, if we were to look back at our data set here, right, if we were going to melt this and we wanted to, say, eventually construct our data set such that it had 1 column for country and 1 column for year, we would say, all right, in this example, my case identifier is clearly this column here, country. My characteristic variable is going to be the year. You can see it's got these sort of back-end stubs here for each year, so we're going to want to isolate those somehow. And obviously, the values are just these things here that come at the intersection of these two axes. So here's the basic call for melt. Again, it looks kind of similar to the dd-ply and the plier calls. The only difference is you no longer need the period in front of the various arguments. You simply put what data set it is that you're interested in melting. This is the name of that object. And you queue in some ID variables. And these are going to be character strings of whatever your column names are, however many you want to actually melt. And there's some other options that you can put on here, like if you're melting a whole bunch of variables into basically 1 column that is the identifier and 1 column that is the actual value, you can change the names of those resulting columns however you like. You can have it return, you can basically melt only certain portions of a data set and then return a subset. The documentation is there, and again, it's pretty simple, but we'll just stick with the basic example here. So if we wanted to take our previous data set and melt it, basically take all those year columns and then have 1 column that has the year, the actual indicator, and 1 column that has the value, we'd do the following call. Melt, our data is going to be WB. This is our simulated data from the World Bank. And the ID variable that we're interested in is country. This is the thing we don't want to melt. And you can see what melt will do is it took all of those different columns, it threw those column names into this variable column here that acts as your indicator, and this is the year right here. Now there's another issue that we're going to have to deal with here. You know, if you tried to plot var 1995, var 1996 somehow, that probably wouldn't work out too well in most software that I know of. So we need to sort of adjust these values here to take off this stub. And there's a very simple thing that you can do, which is kind of helpful. This is the gsub function. And basically what this does is it detects a pattern in whatever you feed into it. In this case, the pattern that we're interested in altering somehow is this stub var with the underline here. And we want to replace it basically with nothing. So we want to take it out more or less. And then, of course, we have to take this variable, and because we want to plot it, we want to convert the class to being numeric. And you can see this is the resulting output. We've managed to take off those stubs right there, and we can do some plotting on this if we wanted to. And you can see we could plot it very easily with something like ggplot. Looks like this. This is what random data looks like. And it's, as we'll see tomorrow, basically this reshape package, it works very much in sync with some higher level graphics program strategies, especially ggplot. So now this is sort of the other way here. If we wanted to take this newly melted data and cast it somehow, there's 2 different kinds of cast calls. that this package has. The first is acast, and the other one is dcast. Again, the nomenclature here, that first letter before cast indicates what you want to turn this object into once you cast it into a different way. In one case, this is to cast something into an array, and dcast is to cast it into a data frame of some sort. Data frames are limited to 2 dimensions in their casting. Obviously, with an array, you can do more. And the basic call, again, it's pretty simple, a little bit more complicated, but the idea behind all these packages is that the syntax is very much standardized, and it's very easy to work between functions. So here, our call would be for dcast. We put in the data that we're interested in casting, and we have to fill in this formula which says, okay, which variables would we like to keep as columns, and which variables would we like to cast as rows? Excuse me, that's the other way around. Which variables would we like to keep sort of varying along each row, and which variables would we like to basically cast up as a column? And there's a basic formula for you to put here. You just throw in the variables that you're interested in keeping within one single column. In this case, it's going to be our xvar, just for an example. And then you put this little tilde right here, and you put the variables that you're interested in sort of casting up into different columns that weren't normally there, aside from on the other side of the tilde. Now, there's this other argument that you have to specify here, which is the aggregate function. So you can imagine if you've got a data set that for each individual row of this data set, say in theory, it's got a lot of different identifiers, right? And you wanted to sort of cast a data set that only cast a certain subset of that total number of identifiers. Obviously, it's not going to be able to identify just one value for each one of the intersections in this table. So unless basically you're casting every single identifier variable, this cast function is going to need some way to take these X amount of values that satisfy the criteria you've put in and come up with just a single value to put in the intersecting cell between the column and the row. So the default, just so you're aware of this here, is it's going to put in the length. So if it's got 50 different possibilities that it could put in here and you don't specify some sort of aggregating function, it's just going to put in 50, regardless of what the content of those actual cells. So this is something you need to be careful with. It won't always warn you about this, depending upon the settings. You can set it such that it will warn you, but just be aware. If you're trying to cast a subset of your total variables, you either do need to explicitly specify the subset somehow, or you need to be prepared to come up with an aggregating function. And you can see when we try and recast our data here, we'll sort of put back this little stub using the paste function, and we're just going to apply that to the old year variable. And then we call dcast here. The data we're interested in casting is this new data set, WB World Bank melted. And the formula, we want the country to be the only column that we really preserve. And we want to take previously the variable column, and we want to basically split it up and put back a whole bunch of different columns on the other side here. And these are the intersecting values. So that's the basic idea of how you take some sort of data set, you melt it into something that you can work with, and then once you're done working with it, if you feel like you need to, you can cast it back into something else. Okay. So now we've gone over sort of 2 of the 3 things for today. The first 2 were very much about sort of working with data, trying to get an idea of what it looks like, trying to make it take on a shape that's preferable for you. And now we're going to get to sort of some of the more basic things that applied people are really chomping at the bit for. And these are going to be things about regression. So the most basic sort of catch-all regression function that you're going to need to know about is called GLM. Chris already showed you a little bit about LM. GLM is it's a very generalized version of that. It allows you to apply a number of different regressions that aren't just ordinary least squares. It allows you to apply things like logit, Poisson, various sort of integral functions. There's a whole range, and it fits a generalized, as I just said, it fits a generalized linear model with your choice of family and length function. And LM is just a subset. If you are interested in just sort of getting used to using GLM a lot instead of LM, just a thing you might want to note, we'll see this in a second, but the family you have to specify is Gaussian, and the link is going to be the identity. Yeah, so this is the basic function we're going to be working with here for a second. So here's your basic call. You have GLM, and this is the formula. This is basically the formula of the line that you're interested in estimating. So you put in your Y variable, your outcome variable of interest. You specify the various regressors or covariates that you're interested in. Again, these 3 points, not a stand-in for different arguments that you could pass for a function, really just to mean that you could specify a formula that goes on for quite a long time. And then you specify the particular family for your regression link, which the way it works is you put the family name first, and in parentheses, you put the link equal to the character string, which is the particular link you're interested in. And then, of course, you have to have some data if you want to actually run this regression. So you specify the data set you're interested in. Now, there's a ton, not a ton, but like 15 or 20 different families and different links that you could possibly use. But in reality, if you're an applied person, you're probably only going to really need 2 or 3. So these ones are the important ones. If you want to run a logit, it's in the binomial family, and the particular link is logit. Again, the Gaussian with the identity link, that's exactly equivalent to ordinary least squares with LM. And another one, if you're using some count data, you could use Poisson, and the link in this case would just be a log function. So, an example. So you saw some of how this works and how the resulting LM object, like what's kind of in it with the example that Chris gave before. So we're going to go through another example here and show that it's very much the same. And this is an extremely silly regression that we're going to run, and probably not one that would be recommendable to anyone, but it's good for pedagogical purposes, I suppose. So the formula in this case, we want to know if you're an old man, what are the best predictors for being an old man on the basis of your party identification, how much money you make, and your religion. And so old man we know is an indicator variable, so in this case we're going to run a logit regression on it. And our data set here is the old man data set. So we stored that particular regression in this object, and the resulting object is going to be of a class GLM. And so if you type in the command objects and then put in this GLM object, it's going to show you exactly, once you run this GLM regression here, what it's giving you. And you see, as Chris said, you get a whole lot of regression type stuff. You've got some information criteria here, the coefficients, this is probably what you're most interested in. You've got the original call that you put in, your data set is there, what you specified as the family, there's a vector of fitted values, you get some R, your Y's, weights if you specified them, there's a whole bunch of stuff. But what you can do is actually, once you have this object, you can specify one of those elements of this, what is basically a list, to actually see what they are. So we ran this regression, the regression's in the object, we want to know what the coefficients are. That's probably the thing we're most interested as a first pass. So we write old man to refer to our object, and we want to get these coefficients here. And it'll basically give you something that looks a little bit like this. Right? And we can do this for all these other things. Here's the residuals, the information criteria is there, and yeah, you can access all parts of the regression object just by a simple call after a $sign here. Now, Chris also told you one of the cool things about R is that it has these functions that are expecting these sorts of objects. You know, if you use summary.glm, it knows that you're feeding into it something that has a very set and specific structure. And it can do some really cool things knowing exactly what that structure is. Like, for instance, taking what is really kind of an ugly matrix of coefficients here. This is really not great to look at. But when you use summary GLM, just like you would use summary for the LM function, it takes the various components of this object, the various parts of this list, and it applies its own set of functions to it which make it look really cool like this. So you see here you've got your list of coefficients, you've got your estimates here, it'll give you z-scores, standard errors, and your p-values, of course, all important p-values, as well as some dispersion parameter, that sort of thing. So that's what it'll get you. And just to note, you can actually sort of take this summary object, which is in itself an object, and pull out different elements of it. So for instance, if we stored that summary as an object, and then we check out what objects are actually in this old man regression here, it itself will store the information criteria, the scaled covariance matrix, some contrasts, the degrees of freedom, all that sort of thing. This is really, really useful if you have like a long list of different models that you want to try and you don't want to have to type them in every single one. You can just come up with this big list, write a little loop of some sort that will repeatedly feed this in, extract, say in this case just the coefficients, and then put them in some object that will store your results. Being able to pull out particular parts of the list is really, really helpful that way, especially from a summary object. Yeah, you can see here, for instance, in the summary object, we took out the coefficients and just printed them right here. So what this is basically now, once it's been stored in the summary object, you have this nice little matrix, right? So I could basically write a function that says, all right, run 1.5 billion regressions, which isn't necessarily recommendable, but you could only pull out this column, for instance, and then aggregate over a series of regressions, that sort of thing. It's very, very flexible. The important thing to just note is that whenever you do a regression, you do have the capability to extract only specific elements of the overall output. Okay, so we've been really bashing on factors like this entire day. They're kind of cool, but they really, mostly until now, have screwed things up royally. So factors are actually really cool in the LM and the GLM context, especially if you want to do some regression, say, with fixed effects. If you wanted to do it by hand, you might think, okay, if I want to do fixed effects for race, I'm going to have a dummy variable for white, I'm going to have a dummy variable for black and Asian, all that sort of thing. A quick shortcut is to really, if it's not a factor already, just say, all right, I'm going to estimate this model, which is y predicted by x1, x2, and the factors of x3. And more or less what this is going to do is it's going to take x3, it's going to do a factor expansion, and your resulting output is going to give you coefficient estimates for x1, x2, and individual ones for all the values, all the factors of x3. So that's an easy way to do fixed effects. And if you want to do two-way fixed effects, there are ways to do that. Probably you don't want to do more than one factor up here. You want to do some sort of demeaning. But again, you have to be careful with your degrees of freedom adjustment. This is just technical things in case you guys are really into fixed effects. But I can send you some resources if you're interested in doing more with that, specifically about the PLM package. So the other thing, you might not be interested in fixed effects, but as good applied researchers, you should always be interested in various sorts of interactions and various sorts of nonlinear relationships. So R has really, the LM and GLM facilities have really easy ways for writing a whole bunch of interactions very, very simply and very, very quickly. And there's two basic ones that you need to know. The first one is where you basically use a colon here and you say, all right, I want to interact x1 and x2. And what this will basically do is it will give me some sort of indicator variable for every combination of values, of unique values in x1 and x2. So for instance, if I wanted to run a regression here, which is, again, we're predicting the probability, this is the propensity score for being an old man on the interaction between your party identification and your religion. You can see here, just by writing that simple interaction, R is going to estimate, it's going to create coefficient estimates for every unique value of party ID. You see you got Democrat, Republican, Independent, all that sort of thing, for every value of religion. And this is an easy way to write interactions. You have to be careful, obviously, if you're going to write an interaction like this, that you're not going to sort of irreparably break your model. But it's a quick and easy way to do it. And there's another interaction, another way to do interactions here, which is to, instead of a colon, put in a little star here. And basically, this gives you the cross of x1 and x2. Aside for, it will give you not just those complete interactions, but it'll also give you the main terms. So for instance, if I interact x1 star x2, it's going to basically estimate a regression that has x1 plus x2 plus all the interactions of x1 and x2. Obviously, leaving out some variables so as to avoid the dummy variable trap. So for instance, if I wanted to, again, regress the probability of being an old man on party ID and religion, interacted with this cross interaction here. It's going to give me just the main term of being a Republican, being an independent, being something else, being Catholic, all these other religious affiliations, and then way down here, it's going to give me all basically the estimable combinations of those unique values that it can actually estimate. Go ahead, yeah?
Is it possible to command it so that it only displays significant coefficients?
I mean, you could write a little function that could eventually get that output, but I think with the summary function, it's going to just the significant coefficients. I mean, you could write something, store a summary object, extract the coefficient matrix, and then basically from that create a subset of the coefficients that are only significant. But that would have to be an additional thing that you'd have to set up yourself. It doesn't come built in, so to speak. Yeah.
On that note, can I just add something? Is that you have to be careful not to interpret the p-values from the output. You have to do sometimes analysis deviance to do hypothesis testing. So you can't really say, oh, that's significant because the table has a star by it.
Well, it's if that variable is, yeah, it depends on sort of what you're doing.
It depends on what you want to do, yeah.
But basically, the p-values there are if you take a model that has all of those variables, all of those regressors, and leave out the one of that row you're considering, which doesn't make a lot of sense if you have factors. In which case, as you say, you want to be doing an analysis where you do like a ratio test, where you take out all of the variables, all of the levels associated with a particular factor variable. So yeah, that's a good point.
Yeah. Again, though, these are really just to show you what's going on in each command line. Not that these regressions are really appropriate to do in any context, and it's important to think about what you put in your regressions. Yeah, but these are just sort of silly toy examples here.
Yeah, sort of the danger here is we're showing you how to do a bunch of computing, and we're not really showing you how to do statistics. And there's a lot of ways you could go wrong with the statistics if you just plot ahead with the computing without knowing what you're doing with the statistics.
Right. So learn your stats. Okay. Now, for a lot of you who are coming from sort of more proprietary statistical backgrounds, which is I guess a fancy way of saying Stata users, if you sort of want to do some regression diagnostics, for instance, there's a nice little drop-down menu with some options. If you want to change your standard errors, you check a box in your initial regression window. So it's not exactly that easy to do those sorts of things with R, but it's still pretty easy. And I want to introduce you really briefly to a package that's really good for doing a lot of these sort of basic stuff, these basic things that a lot of applied researchers are going to be interested in. And specifically, the package here is lmtest. And this has a lot of different functions that you can run on a regression output, on an GLM output. And it will give you some nice little statistics to actually do, the good statistic part of figuring out whether or not you're using these fancy computer tools for doing things correctly. So, for instance, if you wanted to estimate a BP statistic for heteroscedasticity, you simply load lmtest, and then you call BP test, and all you have to put in here is the object in which you stored your regression, and it will spit back out the specifics of the test. Yeah, so that was the BP test there. That was listed twice. So there's a whole lot of tests. You can have a Durbin-Watson test, for instance. And one really important thing that people are interested in, especially if you're using something like where you're worried about heteroscedasticity in your errors and you want to estimate some sort of robust variance-covariance matrix, you can again take this object right here, put it into this function called coef-test, and specify a particular type of variance-covariance matrix that you want to include in calculating your standard errors and coming up with these p-values, for instance. And it will take that object and give you a summary output here with adjustments made to the standard errors. So it's not quite as easy as ticking a box, but still very much doable. And for people interested in panel data work, if you use something like the PLM package, it also has capability for doing panel-corrected standard errors in addition to the heteroscedasticity and autocorrelation robust standard errors. But for that, it's probably best implemented in PLM, which I'm not going to go over today, but it's good to know that it's out there. So this is the breakout and overnight homework. Well, before I get on to this, are there any questions on the particular functions that I showed you? None? Okay. So this breakout question does not come from me. This comes courtesy of Chris. So consider the voting preference data that we've been working with here. What we'd like you to try and do is fit a logistic regression to the data from California, which is state number 5, modeling the preference for voting for Bush. Again, this is Preso 4 equal to 2, versus Kerry, removing all the other candidates as a function of income and with some other covariates as you find interesting. And see if you can report those things. And then we want to see if you can basically give us an object that's going to predict, it's going to come up with a predicted propensity to vote for either Kerry or Bush. So.
Yeah, so let me jump into a few final comments. Unless did you have anything else you wanted to say, Chris?
No, I think that's better.
Okay. Let's see. So, sorry, I'm tired. A few final thoughts. One is it's been a long day, so in terms of the breakout and the overnight homework, a few of us will be around for a little while longer. So if you do want to hang out here and try and work through some things while we're still here and able to answer questions, you're welcome to do that. You're of course welcome to leave. You've been here for a long time. The second thing, you can see on the schedule tomorrow what the plan is for tomorrow. It's essentially going to be what's on there, and plus I'll talk about the stuff about packages that I didn't get a chance to talk about today. The other thing I want to point out to you is if we go to the GitHub site, hopefully this is going to work here. Yeah, okay. So for those of you, I know some of you probably won't make it tomorrow. For those of you who are going to be here tomorrow, we're going to leave some time to fill out a feedback form during one of the breaks tomorrow, and we'd really like your feedback. This is the first time around. It'll be good to get your suggestions and your thoughts on what went well and what didn't go as well. But if you're not going to be here tomorrow, I do ask you to and encourage you to go to this link and fill out this form and give us some feedback, just so you know that this is here if you're not going to be back here tomorrow. Anything else any other questions or anything? Any of the other counselors have anything to add at this point?
I might just add, if you haven't got Git installed on your computer, you might want to try to do that because I'm going to talk about it a lot tomorrow, and I'll do that for you tonight.
So you're going to be around for a little bit to help people? Okay, and also, we'll be here. Oh, the other thing is we're going to start at 9 tomorrow. We'll give you a little more time on a Sunday morning. But we'll be here by, say, 8:30 or so. Does that sound fair? So if you want to try to install Git tonight and have troubles and come in by, around 8:30 tomorrow, we'll be here to help as well.